Okay, then we will jump into day 3. And like I mentioned yesterday where we left off, we're going to start off by just jumping right to the walkthrough for phase 4, where we're going to change the model a little bit by kind of condensing things down, where we're going to remove the redundancy of having 3 source activities, and we're going to take it down to a single source, and also use labels and the decide activity to help us route tokens of the correct type to the correct flow. So if I were to come over to my model, the first thing that I might do is just delete a bunch of these extra pieces. And I'm also going to get rid of that connector just so I can remake them. And so instead of having this be the start of phase 2, I'm going to say that this is going to start all my phases. And instead of just creating my phase 2 tokens, I'm going to say this creates all my tokens. And I'm also changing the arrival rate here to be a scale of 15. So one thing that's kind of interesting about this is that when we had 3 sources, each source had its own arrival rate of on average every 30 seconds, right? That meant that the creation of each of the tokens that flowed through my 3 phases were being created independently of each other. And so they all had about an exponential distribution towards arrival, but they're all independent of each other. And so they all had their own arrival rate, their own arrival times that was independent. But by going down to a single source and increasing the arrival rate, I'm trying to get a little bit closer to having an arrival of a token similarly to what we had with the 3 sources. Because when we had the 3 sources with their own inter-arrival times, our true arrival rate of things into the system is actually much faster than every 30 seconds because they were all operating independently of each other. So by going down to a single source, I might have to think about how this impacts things like the arrival rate and how to account for now having one source that generates a thing and then have that thing be randomly assigned to one of my 3 flows rather than just creating something that always goes to the same flow. So just a slight modification here to increase the arrival rate. And in this container, I'm also going to bring out my assign labels activity. Now, one thing that as far as like documentation goes, when I make an assign labels activity, I tend to like to put the names of the labels that I'm going to assign into the name of the activity, so that if I'm looking at the flow without looking at the properties of the individual activities, it's nice to be able to see, oh, this is where I assigned the label called type, right? And so if you add multiple labels, it might be good to add multiple, the names of all those labels in the title of the activity. It just might make it a little bit easier to follow. In this case, it's pretty straightforward. We just have the single label that we're calling type. So I'm going to say that my label name is type. And then I need to set my value. Now, in the description, it said that the value of type should occur roughly evenly. So we have 3 different values of types 1, 2, and 3, and we want them to occur roughly 33% of the time each. Now, there's 2 ways that you could do this. Most people do it this way, where they went to the value drop down, they go to the by percentage option, and then they would have their 3 percentages. You would say something like 33 gives you a value of 1, 33 gives you a value of 2, and 33 gives you a value of 3. Now, one thing, though, to point out here is that this only adds up to 99%, technically, right? And so that would mean that you would have a 1% chance to actually assign a value of 0. So when you're dealing with these percentage-based options, you need to make sure that the percentages add up to exactly 100%. So that means that one of them has to either be a 34 to account for that 1%, or you could even give yourself some more significant digits and say like 33.3, 33.3, and 33.4. Again, just to make sure that it adds up exactly to 100%. Okay, so that's kind of the downside of using the percentage option. You just have to remember to make sure it adds up exactly to 100%. The upside is that you get to define exactly the values that you want, right? You can have your values 1, 2, and 3, Could also be 369 or any other values that make sense for your model. And so this is the way that people typically go on this on this example. For those of you that got this far, did you do it this way or did you do it a different way?
I did the 34.
I did
3.
the 33.3.
Cool. Yeah. Now, the other way that you could have done it, that would have been an okay way to do it as well, would have been to use a distribution called D-uniform. Remember, we introduced D-uniform on Monday, where you could have said that you have a minimum value of 1 and a maximum value of 3. Because the way the D-uniform distribution works, remember that the D stands for discrete, which means integer values only. And because it's a uniform distribution, it means that it's an even distribution of the 3 possible values, where they all have a roughly equal chance of occurring. So this would have been fine as well. And so the upside of this is you don't have to worry about managing the percentages. The downside is that you have to establish a minimum value and a maximum value, and the valid values have to occur within the range. So like the by percentage option gives you a little bit more control over the values themselves, but you have to manage the percentages. D-uniform gives you less control over the values, but takes care of managing the percentages for you. So it's kind of a, whichever way makes the best sense for your model, but it's good to know that these sorts of things are kind of equivalent. And remember too, that it might be useful to use that label as a way to assign colors so that we can visually verify the flow of the tokens. And kind of going back to, I think it was Connor's question about debugging. This is a very common type of strategy to kind of validate models, is to assign colors to things and make sure that things that are the right colors are in the right places. So I'm going to go ahead and do that, like we talked about yesterday, where I go to my properties panel and I see that I'm in my process flow properties. And I'm going to click on the button for more properties, which brings up this window. And under the visualization tab, I'm going to say that my token colors are assigned according to my label called type. And so if I just kind of see where I'm at, if I hit reset and run, I'll see tokens coming to the assign labels activity. And as they get assigned their label values, their colors will be updated, such that I can look at a red token and know that its type value is 1, green tokens are 2, and blue tokens are 3. Okay, and so now what I need to do is I need to get those tokens into their right flow. So I need to make sure that things that are type 1 go to phase 1, things that are type 2 go to phase 2, things that are type 3 go to phase 3. So this is where I need to bring in my decide. So I'll pop in my decide activity. And I'm going to make my container just a little bit bigger, because containers get upset if the activities are not fully encompassed inside of them. So I'm just making sure that the activities aren't touching the borders of the container. And then I just need to draw my connectors. You can draw your connectors either from the decide activity like we talked about, or you can also do it from the container itself. Either way is fine. And if you want to kind of adjust what things look like there, that's also just fine. I like moving around the ends of the connectors so that it looks nice. And now in my decide activity, I need to say that we're deciding by type. And then in my send token 2, we're going to say that we are going to choose a connector by case. My case function is going to be based on my type label. And then I have 3 possible values of type. If type is equal to 1, I want to use connector number 1. If type is equal to 2, I want to use connector number 2. And if type is equal to 3, I want to use connector number 3. And I chose 1, 2, and 3 here because that's the way that I connected my connectors. So if we zoom in here, we can see that my first outbound connector is leading off to my phase 1 flow. My second connector is leading off to my phase 2 flow, and my third connector off to the phase 3 flow. Now, you wouldn't have to set it up that way if you didn't want to. Like, for example, if I'd said instead that, like maybe my first connector out goes to phase 2, and my second connector out goes to phase 3, and my third connector out goes to phase 1. Well, now I've changed the sequencing of the outbound connections, and so I would need to make that agree here. So now I would say, well, if token.type is equal to 1, then your connector is 3. If you're a 2, your connector is 1, and if you're a 3, your connector is 2. Right, and it's fine to do stuff like that, right? We're just kind of establishing like a map relationship between the values of type and the values of the connector. They don't have to be the same thing if you don't want them to. I just tend to do it that way out of habit, but there might be good reasons where you might need to do something like this instead, where case 1 actually matches up with connector 3, or case 2 actually matches up with connector 1. Does that make sense? Anyone have any questions there? Okay, so let's see what it looks like then. So if we hit reset and run, we should see red tokens always flowing down the phase 1 flow, green tokens going down the middle, and blue tokens going down the phase 3 flow. And that looks like what we're seeing. So we can be reasonably confident that the behavior of the model, though changed slightly, is still giving me the same results that I had before with the three independent sources, but now down to a single source that randomly assigns the destination essentially to the token. And so this becomes a really common way that the decide activity gets used in conjunction with labels, especially where the decide activity could tell you where tokens may need to flow based on some set of conditions. Okay, any questions there at all? Good deal. All right. All right, so with everything that we've discussed so far, we're kind of trying to establish the basics of working with process flow. So getting used to thinking about things in terms of tokens and activities and the shared assets here in the case of the resource, where we're thinking about how to manage flow, how to manage behavior for tokens as they go through a set of activities. But so far, we haven't really talked about how this integrates with the 3D world at all. And like I mentioned yesterday, one of the nice things, one of the most powerful things about process flow is how well it can integrate with the 3D environment. And so I want to discuss a couple of different strategies that there are initially here that allow you to integrate process flow based logic with object based logic. And then we're gonna discuss a couple of different strategies for that. This first one is going to be what I call kind of like the more process flow centered approach, where we have the ability for process flow to actually control 3D objects. Now, remember that objects on their own already know how to execute a certain set of events. And so these activities allow us to cause events to happen on objects, essentially, where instead of creating flow items with source objects and moving them around using port connections, we can use activities that allow us to create and move flow items around the model manually so that we can bypass certain aspects of the built-in object behavior and have more control over what's happening using this process flow centered approach. So in this example, process flow is going to be doing most of the heavy lifting, and the objects will be used mostly just as a visual of what the logic is actually doing. Now, I will say that this is a fairly common approach, and it is actually a preferred approach by some of our consultants, where they like the fact that they can start out with a process flow based model that's very simple and abstract, and then they can add in 3D capabilities where needed without having to go back and think about how some 3D behavior is going to alter their flow. It allows for them anyway, a more natural progression from abstract to more concrete. So that's the first approach I'm going to show you here. And it takes advantage of a set of activities that allow us to work with objects. And the big three that we're going to be talking about initially are the create object activity, move object, and destroy object. And so these three activities allow us to bypass certain aspects of the object environment, like how create object allows us to create objects from the 3D library, allows us to create flow items. Move object allows us to move those objects around, and then destroy object allows us to remove them from the model without having to send them to a sync object. So let's take a look at how each of these activities work in kind of a simple environment. So I'm just going to stop that. And we'll come back over to a little example model. And let's say that I have just a couple of queues here. And I'm using queues for this example because queues are relatively simple objects. They don't have a lot of events that they execute. And so if I'm going to control my 3D visuals using process flow, generally speaking, it is easier or better to use simpler objects so that process flow doesn't have to interfere with their event execution very much, or we don't have to worry about, how's this going to interact with like a processing time or a separator or a combiner or something like that. So using just queue objects, in this case, I'm using them as locations where I may want process flow to move flow items around for me. So I'm going to start my process flow by just having a source activity. And I'm going to say that there is a delay right after that. And then we're going to say that there is another delay. And then another delay. And then a sync. And so right now, I haven't done anything that talks to the 3D environment at all. In fact, if I hit reset and run, we'll see that the objects don't do anything because they aren't receiving flow items. And remember, that's one of the big key features of the 3D objects, that if they don't have any flow items, they don't do anything. And so if all of my logic is handled over here by my activities, then those are the only events in my model. So if I want to create some flow item flow to match my token flow, I can use the approach where I use these object-based activities, create, move, and destroy. So let's take a look at create object first. So I'm going to bring out create object, and I'm going to put it right before my delay, my first delay. Now, if we look at the properties for create object, and again, you can either do that on the right-hand panel, or you can click on the icon to bring down the properties. The create object activity would seem to have a lot of inputs, but they're still all focused on how to create an object. The first thing that the create object activity wants to know is what kind of object are we going to make, right? And so by default, it says that you're going to create a box. And this is a box from the list of flow items that we have available to us. Now, if you want to create a different object, then you would go to the drop-down menu and see that there are other options that allow you to create objects in different ways. So notice that there's the ability to create objects from the library. So if you wanted to create like a processor, create object would be happy to do that for you. That's not very typical though, but it is there. But under the flow item section, you can see that there is the full list of different flow item classes, just like what the source object provides when you want to choose to create a different kind of flow item. And so if you wanted to create one of these different kinds of flow items, you would come to this menu and then this sub menu and choose what flow item shape you want to create. But we'll go ahead and leave it on box for now. That's going to be fine for what we're doing. And then we have a quantity field that gives us the option to decide how many of these flow items we may want to create. By default, the quantity says 1, assuming that one token is going to create one flow item, or one box in this case. Because remember that a token has to arrive to the create object activity in order to cause that object to be created. So this is as if then that the tokens, as they flow through their flow, are going to create flow items as they move around the model. And so the most common thing here is to leave the quantity at 1. but you do have the ability to have this be a different quantity, including the use of statistical distributions. If you want one token to create a random number of flow items, that would be fine. Now, the next property allows us to indicate where in the model the object should be created. Now, right now, it just says created into the model, which would place the flow item at the 0, 0 coordinate in the middle of the grid, which is right here at this, this heavy black cross. You can change this creation destination so that you can tell the object that gets created to be placed either inside another object, which is the most common, or to be created at the same XYZ coordinate as the given destination. Okay, so what's the difference? Well, the difference is that if you say create in, that means that the flow item will be literally placed inside the object, which will cause the event system of that object to begin to execute. If you say create at, that means that just visually it'll be located at the same coordinate as the object, but not inside, and therefore the on entry event and the other events that come after on entry will not fire. Okay, so create in is much more common than create at, because create in, when we do creating flow items like this, generally we want them to go into objects so that the objects can execute whatever events we need them to execute, and also so that it looks more like what we're used to seeing in a 3D model, right? Like yesterday when we were working with the 3D objects, when a source object was sending flow items to a queue, those flow items were literally inside the queue, right? And that's what causes the event system of that object to happen. So we're kind of mimicking that same behavior here without actually having to use port connections or anything else. We can just say create it inside some object, and then we're going to do something else later on. So for this example, I'm going to say that my target for create in is going to be found by choosing Q1. So I'm going to use the eyedropper and select that first option that fills in this purple text that says that we are referencing Q1, the object called Q1 in the model, and that will be our target destination for the creation. Okay, does that make sense so far? Anyone have any questions? Okay. Now, the last important property for the create object activity is this field that says assign to. Now, this idea of assigning to, this is going to show up on a lot of different activities. In process flow activities, we very often give you the ability to assign labels to the tokens that execute these activities. And so wherever we give you the ability to do that, we have this assign to field, and it says that the label that gets assigned is going to be named, in this case, item, which will be assigned to the token. So that assigns a label called item, but what is the actual data? Notice that there's no value field here, like with what we saw on the assign labels activity, where I can't choose some value that I want to be assigned to the label called item. That's because the create object activity is going to assign data by default. And the value that gets assigned here is going to be a reference or a pointer to the item that was created. So this mechanism allows there to be a relationship between the token and the flow item that it creates, and that every token will have a unique reference to the unique flow item that it actually created. And that's going to be important because there's going to be other activities where we can use that reference as an input in order to say, when you do this activity, do something to my item. Okay, so let's kind of see what that would look like. So if I hit reset and run right here, and actually I won't even run, I'll just step forward. I'm just going to step forward one event so that we get our token. And the token is currently at the create object activity. Nothing is in the 3D environment yet, except for my 3 objects. But when I step beyond the create object activity, now I get a flow item located inside of Q1. And I can tell that it's inside of Q1 because if you look at the queue, you can see that its throughput statistic is updated, its content statistic is updated. And if I move the queue around, the box moves around with it because it is literally inside the queue is acting as a container for this flow item. Just like with what we saw in all of our object-based stuff Monday and Tuesday. Now, if we take a look at the token, we'll notice that there is now a label that references that flow item. So the item that is associated with this token is named box1, and it's located inside the object called Q1. And so this unique reference points to this unique flow item in the model. So this token knows that it belongs to this flow item. Or you could also think of it as this flow item belongs to this token. Either way is fine. The important thing is that the token knows what item it's associated with. Okay, now if I just reset this and let it run, I want you to notice that the flow items get created into the queue and the tokens just continue moving along, right? So far, the only thing that I've told the flow items to do is to be created. And they're just being created into the queue. And since there are no port connections on this queue, they don't know that they're supposed to go anywhere. They don't know they're supposed to do anything. And so the queue is just happily receiving those flow items and executing its stacking animation so that the flow items look nice inside the queue. But the tokens continue on and do all these other activities. Because again, the assumption that we made when working with tokens and flow items, objects, and process flow together is that we don't want to assume how those tokens and flow items are going to interact. And we really put the control in the user's hand to decide exactly what you want to do. So even though the tokens created these flow items and the tokens go on and do other activities, that doesn't necessarily tell the flow items to do anything unless we actually give the flow items some kind of instruction. Okay, so what if we said then that when tokens come to this middle delay, that we want the flow items to go to Q2? And let's actually make it a little bit more interesting. Let's put a restriction on this and say that we have a resource that needs to be acquired. Kind of like our current model. And we'll say that there are 3 spots available on this resource. So if I say that there's a count of 3 here, that means that 3 tokens could potentially acquire this resource at the same time. And I want to say that tokens cannot be moved into Q2 unless they successfully acquire the resource. So if the resource lets the tokens in, then the flow items need to be able to go to Q2. So kind of what I'm doing is I'm creating like a relationship between the resource and the queue in kind of an abstract way, where I'm saying that you can't go to the queue unless the resource says it's okay. So I'm going to grab the move object activity, and I'm going to put it right after the acquire. Because remember that the acquire activity kind of behaves like a gatekeeper that says that if the resource cannot be acquired, you have to wait your turn. And so by putting the move object after the acquire, I'm essentially saying that you can't move your flow item unless the resource is acquired by the token. Because the job of the move object activity is to move a flow item from one location to another. So we're going to say that the flow items get moved out of Q1 and placed into Q2. So in order to do that, we look at the move object properties, and you'll notice that it takes 2 input properties. We have the object that needs to be moved and the destination where we want to send it. So this is where that label that we set up on the create object activity is going to come into play, where the object referenced by token.item is going to be the thing that we move. So since every token refers to a unique flow item, we're going to say that whatever your item is, that is going to be moved into some destination. Now notice that the destination field assumes that we have a label called destination on the token. But if we take a look at our tokens right now, remember that we don't actually have a label called destination. So that means that what's in there by default isn't going to work. And we're going to need to replace this with some destination. So just to make it easy, I'm going to use the eyedropper and say that we want to move things to Q2. So now our item gets moved to Q2. So let's see what that looks like. So now if we hit reset and run, the flow items will stay in Q1 for the duration of the token's delay. And then when that delay is over, if they successfully acquire the resource, we can move them to Q2. And notice that every once in a while, like right here, we get a token that can't be moved because the resource is in full use. Now, that is not the same thing as the content of the queue, right? The limit of 3 here is based on the resource, not the limit of the queue. So we have a whole bunch of things in the queue because these flow items were left in the queue after the token released the resource. So if we want these flow items that are in Q2 to move on to Q3, then I would just need another move object. So we'll say that after the delay at the resource, we're going to move our items now into Q3. And so now what we'll see is that when that first flow item gets moved into Q2, it will only be there as long as its token is doing the delay. So now it gets moved over to Q3 because we said, hey, that delay is over. So now you need to be moved to some other location. So now the content of the resource is the same as the content of the queue because I put in this additional move that said, hey, when this delay time is over, you got to go. Okay, now also notice that the flow items in Q3 are still in the model, even though their tokens are going to the sink. Because again, we didn't assume that just because a token is removed from the model necessarily means that a flow item needs to be removed from the model. There might be things that the flow items need to do that is independent of what the tokens are doing. And so if you want your flow items to be removed from the model at the same time as your sync, then this is where something like the destroy object might be useful, where you might bring in a destroy object activity and say, after that delay is over, destroy your item and then remove the token from the model. But we do the destroy object first in this case so that the token still exists before it gets to the sync, right? And so now what we've got is a pretty good mirror. The flow item flow now looks a lot like my token flow, but it's all being controlled using these create, move, and destroy activities to control what's going on here.
Hey, Regan, quick question.
Yes.
On Q2, I missed a step. I was trying to keep up, but where did you set that the Q2 only holds 3?
I didn't. The resource is doing that. The resource has a count of 3, and that's what's controlling access to the queue.
Okay. So that's what I did, but it was behaving a little different. Well, that's okay.
Did you put in the move objects after the release?
Yes.
And what are you seeing in Q2? Are you seeing 3 flow items, or are you seeing more than that?
Hold on, let me reset and speed this up again. Now I'm seeing 1 item in Q2.
Sounds like then that your count is just set to 1. Did you set your count to 3 on the resource?
Count is 3. And then the acquire should be on the acquire on the second step. What is that supposed to be 3 or is
No,
1?
that's supposed to be just 1.
Okay. There's a mistake. All right. Sorry.
Yeah, so what you had done is you had made it so that a single token consumes all three resources at once, right? So if you change the quantity on the acquire, that means that one token is trying to acquire multiple slots in the resource. And very few times have I found the reason to actually change the quantity on the acquire. That's why I didn't even mention it, because I hope that you guys wouldn't see that it's there. But the count on the resource is what generally we use to control access.
So I got a question. I feel like I got mine set up just the way it looks like up on the screen, but I'm not getting anything to Q3. So I have
What does your move object say?
when I double click on it, it's called move object. Objects is token.item and destination is Q3.
You don't have the checkbox preserve global position check, do you?
That's unchecked.
Okay, it should be unchecked.
Yeah, it's nothing moving over there.
Do you mind if I take a look?
Yeah, let me, can you see it?
Here we go. It's loading now. Okay. Okay, just reset it and let me watch for a second. Click in your process flow just to close that window. Okay, so. All right, I think you've got a buggy connector. So this is something that you don't know to look for unless someone tells you. So go ahead and reset your model. And what I want you to do is to grab the arrowhead on that connector that leads into the move object. So click on the arrowhead at the very bottom of it, and just click and hold and like kind of drag it around, and then drag it back. And now let's try it again. Yeah, there we go.
Cool. All right.
Yeah, so sometimes that can happen, and I haven't been able to figure out a set of reproduction steps to make it happen consistently, but it happens to at least one person in every training class, where even though you have a connector that led into move object, the connector thought it was still connected to the delay, and so the move object was actually being skipped.
Yeah, so I had delayed and sync, and then as we progressed, I moved move object right on top of it.
Yeah.
I didn't remake the connection.
Yeah, so I mean that should be okay, because you're allowed to move activities around in a block and like drop activities on top of a block, and the connector should just like figure out what it's supposed to do. So it's kind of a weird one, but if ever, so if you ever make an activity and it seems like that activity is being skipped over, just kind of, give that connector a wiggle and put it back, and that should fix it. So yeah, not your fault. Okay, so we're doing some pretty rudimentary stuff here where the token is causing the object to be created, the token is causing the object to be moved, and then the token is causing the object to be destroyed. And there's other things that you can use these label references to items on the tokens for. Like, for example, there's another activity that might be really useful called change visual, where you could say that there is some visual aspect of the object that needs to change. Like if you were to say set object color here, you could say that the item is going to be assigned a random color, so that when we run this, we have multicolored boxes because the tokens are creating the object, and then they're causing the change visual to happen, and then so we get these different colored boxes. And so that's another example of where using colors might be a way to make sure that things are working the way that you expect. Set object color is a pretty basic way where it lets you choose a color from a list. But another thing that you might do is to use something like set color by case, right? Where you might use a by case style option, like when we did connector by case on the side, to set object colors. You would just need to say that this is the value, usually a label. This is assuming that the label is found on the item itself, but it could also be a label that's found on the token. and then the item gets changed its color, and then you can choose colors based on, these different cases and things like that. So that might be a way where you might like synchronize the colors of a token with the colors of a flow item, or vice versa. Okay, so a lot of activities that involve objects will ask you first to say, what object are we working with? Like in this case, where it says item, in order to do either a move or a destroy or a change visual, something like that, where you can say that this item that is assigned to this token is going to have something happen to it. Okay, so in order to get us some practice with this idea, I'd like for you guys to do a little exercise where we are going to create queue objects that represent locations where our 5 processes take place. So we're going to have a location where cutting happens, where curing happens, inspection, painting, and polishing happen. Then we want to use the create object activity to create a flow item that corresponds with each of our model's tokens. We'll use the move object activity to move a token's flow item to the correct location in the model after the proper resource has been acquired. And then we'll use the destroy object activity to remove a token's flow item from the model right before the tokens are sent to the sender. So you might do something that looks like this, where we just have, these 5 queues that represent the 5 locations. Might also be useful to create a 6th queue that represents the origin point for all flow items. So I called it inbound parts. And so that might be the place where you say, when I create an object, create everything into the same location, and then move them to the appropriate station based on the tokens acquiring the right resources in your process flow. Okay, does that make sense? Anyone have any questions there?
Hey, Regan.
Yes.
This is more of a generic question, just to wrap my head around why would we, let's say, do a model like this in terms of having the queue objects, but there's nothing that connects on the 3D side, but we have the process flow side that enables all the movement. In terms of, can you tell an example where we can use something like this to create a better model, which we can't do it in the 3D space?
Yeah, that's a good question. So basically with this approach, what I'm trying to do a couple of things. First of all, I'm trying to introduce activities that allow process flow and objects to interact, right? And so the create, move, and destroy objects are the simplest version of that. So we're just kind of getting used to that idea, first of all. But as far as the overall concept goes, like you said, why would you build a model using this approach? Part of it is a particular modeling style that a lot of modelers like. And that approach is to start with the simplest version of your model first, and then add detail and complexity as it becomes apparent that you need it. And so typically that is a little bit easier to accomplish with process flow first as your first step, because it's a little bit easier to construct the abstract skeleton of logic using process flow activities and then add objects on top of that than it is to start out with some objects and some process flows side by side. Unless you are have a pretty good idea of where you're headed and you can kind of do both things simultaneously. But like I said, it's a particular modeling style that a lot of people kind of gravitate towards. But it's just one way of approaching things. And so, like I said, with this model, I'm trying to introduce that modeling style, as well as introduce these activities that allow you to work with the objects. And in the next phase, we're going to look at a more hybridized approach where you have object events playing a much larger role side by side with process flow events. So this is kind of like baby steps as we start moving forward into things that are more complex approaches.
Got it. Yeah. Thanks.
Yep. All right. I would expect this probably to take around 15 or 20 minutes to do. There's a lot of clicks with this one because we're adding a lot of new activities and some new objects. So if you get stuck or have any questions, let me know. And then we'll just be ready for the walkthrough again in about 15 or 20. All right, so to do the walkthrough for this one, again, we're just kind of building on top of what we've already got. And so I'm going to start by creating the queue objects that represent the locations. So my Q1 is going to be used as my my origin or my creation point. And then I'm just going to create each of these queues to represent the locations where these different processes need to happen. So just kind of setting them all out there. Okay, and again, no port connections because I don't want the standard object port connection logic to manage the movement of flow items. I'm going to handle that myself using the flow or using the process flow. So, whoops. My first step then is to create my flow items. So I'm going to come up here to my start area, and we're going to enhance this by adding in a create object activity. Now I'm going to put in the create object right after I assign my labels. And also, in addition to creating an object where I'm going to say this is create object flow item, I'm going to make this a little bit bigger again.
Is there a way, like if you put that precise and you accidentally drop that right above the assign labels, is there like a little button, like up down arrow that you press to just move it up and down in this block?
Yeah. If you hold down the control key on your keyboard and click and drag, you can change the sequencing of activities in one.
Yeah, that would save me a lot of time.
Yeah. So, and then after I create the object, I'm also going to throw in a change visual because I want to color my flow items to be the same as my tokens. So I'm going to say color flow items as tokens, something along those lines. So for my create object activity, I'm going to create a box. That's fine. If you want to change the shape of the object, that'd be fine also. And then for my create in, I'm saying that we're going to put this into Q1. And I'm going to keep the label name for item the same. I'm going to keep it on the default. You could rename the label here if you wanted to, but it's not required. You would only change the name if the term item is maybe too like abstract and you want something that's a little more concrete, like maybe you would call it like part or something like that. That would be fine too. But I'm going to leave it on item. And then for my change visual, I'm going to do a set color by case where the value is going to be my type label that's found on my token. The object is going to be my items. That's going to be the thing that receives the color. And then I'm going to add 3 cases where if token.type is 1, it's going to be a red box. If it's a 2, it's going to be a green box. And if it's a 3, it's going to be a blue box. And that just makes sure that my tokens and the corresponding items are always going to be the exact same color. Because with the default color sequencing that the process flow coloring of tokens uses, that means that type 1 is a red token, type 2 is a green token, and so on. So I'm just keeping that same pattern over here. And then in each of my blocks, I need a move object. So I'm going to drag move object and just drop it right in between the acquire and the delay. And we're going to say that this moves the item into my inspection station, which is Q2. And then I'm going to move into the painting station, which is going to be my Q3. And then I'm going to move into curing, which is going to be my Q4. And then we'll move into cutting, which is going to be my Q5. Move into inspection, which again is Q2. Oops. And then we'll move into polishing, which is Q6. And then again for cutting, into Q5. And again for painting, which is Q3. And again for curing, just Q4. And finally, back to inspection, which is Q2. Now I also want to destroy my flow items. So I'm going to bring out a destroy object. I'm just going to put that right on top of my sink. And destroy object is just saying that we're destroying the item. And so since I didn't change the default label name, that's going to work just fine. And remember, the destroy object in this case goes first because the token needs to exist in order to tell the object to be destroyed. And so now when we hit reset and run, we should see red flow items that correspond to red tokens, green flow items that correspond to green tokens, and blue flow items that correspond to blue tokens. And they're just happily moving their way through the flow until they reach the end, and then they are destroyed and removed from the model. Now, one thing that was a question that did come up, and I want to point it out right here. Devin had asked, is it bad that there are 2 flow items inside of a queue that should only have one thing? So this represents inspection, and we've got 2 flow items in there right now. But the reason why is not because these 2 things are processing at the same time, but it's because we have things that are delayed, waiting for their turn for the next resource. So these 2 tokens actually correspond with these 2 flow items. And the only reason why I know that is because I know what to look for. But if you wanted to kind of figure out, well, how come these two flow items are inside this queue when we said that, you know, the resource should only allow one thing in the queue at a time? Well, it's because that these tokens here were in inspection in the previous step. They released their control over the resource, and then they tried to acquire painting. But as you can see, painting is in use by another flow item right here, represented by this token, which means that these 2 flow items are still in the queue waiting to acquire, because we don't allow them to move to the painting station or anywhere else until after the resource is acquired. Okay. Now, this is a result of just the way we decided to handle acquiring and releasing. If you didn't want this to happen, if it was inappropriate that waiting flow items were waiting at the station where they were processed, then you might want to change the sequencing of the acquire and the release. Like, for example, simply, you might do something like this that says, well, let's acquire first and then release second. Now, if you do this, we have to think about what this release is actually releasing, because you'll notice that it says that we are releasing the last acquired. So if we left it the way it said here, then that would mean that we'd actually be releasing the painter. So what you'd want to change this to is to say release the first acquired, to make sure that you actually released the inspector, which was acquired first, versus the painter that was acquired second. Remember, we kind of talked about this yesterday, where by default, the release activity releases the most recently acquired resource. So if you flip the order of these things, where you say acquire, delay, and then acquire your next location before you release your current location, you would need to think about what is the appropriate resource to actually release. Would it be the first acquired, the last acquired, or release everything all at once? Right? There's some different options here that we didn't talk about. So this is kind of a good reason to introduce this idea. And so this would mean that we would rethink the sequencing of the acquire and the release portion of this model if we don't want to see flow items that already finished their delay waiting in a station like the inspection location before being allowed to move on to their next station. Does that make sense?
Yeah.
Yeah. Hey, Regan, I put
Yes.
the move object after the delay. Is there like a difference between it being before or after?
Yeah, it could be a pretty big difference visually, because what that would
Okay.
mean is that you would do the delay time before you actually get moved into the location. And And so if what we're trying to represent is that the flow items go to a station and then perform an operation there, then we definitely would want to move it to that location before we do the delay.
Yeah, so what I did was I created the flow item, and then it went through the delay, and then I moved the item to the next spot, and then it performed that item, or performed that delay and then moved. So but it did match what it looked like the tokens. If that makes sense.
Yeah, I mean, it definitely could be. I mean, there are multiple ways to skin this particular cat.
Okay.
But as long as you account for the movements and the tokens are representing where things are the right way, then it's probably fine.
Okay, cool.
So again, the question of when is the right event, or where in the sequence is the right time to do an acquire and a release, that's going to be largely up to you. And that's one of the nice things about working with the shared assets and process flow, is that you get to decide what makes the best sense, right? I mean, because like I remember a long time ago, before we had process flow, I was working with a client, and they had these workbenches where people stood and they just performed these little work orders that showed up. They were like assembling. They had like a bin full of parts, and so they would like receive a work order, and they would receive something that was partially built, and they would tack on their pieces before sending it away. And the workbench was really big, and so in their model, I'd initially represented their workbenches as just processors. But visually, it didn't look like how they wanted it to, because they would say, well, there's the possibility that even though they got done working on the thing that they were working on, they might just push it to the side of their workbench and wait for someone else to come and pick it up later. But it doesn't stop them from working on the next thing that they wanted to work on. And so, like with the processors, the default mechanism for handling things like acquire and release, like if I just put together a quick little model here. So when you think about it, the job of a port connection in a model like this is to manage acquiring and releasing this processor. Actually, let me make this a little bit different. Let's add a second processor here. Illustrate this a little bit better. And we'll say that the second processor has a longer processing time, just so it's more obvious. So when we have flow items going through here, if you get to the point where the upstream flow item wants to acquire the downstream processor, the assumption that the port connections make is that if you can't acquire the downstream processor yet, then you just stay in your location, and that blocks any further upstream flow from coming to processor one. Right. And so when I was helping them kind of put together their the beginnings of their model, they said, well, we can't do it like this, because there's actually, even though you're done with your processing time here with this flow item, you could start working on the next thing. It was okay that the previous thing that you worked on was still in the same location as the process. So this is assuming that if the flow item is present, then we can't receive any additional flow items. Right, that's the default behavior of the port connection, working with object properties like the maximum content that say, okay, you can only work on one thing at a time, but if you finish the one thing, then you can start the next thing, right? And the processor doesn't have a built-in way to handle that kind of a behavior. So in that case, I needed to kind of work around the system, because I didn't have process flow yet, to mimic the behavior where there could be at least one piece of work waiting for them on their workbench, waiting for them to do something while they're actually working on something, and something is actually still at the end of their workbench waiting to get picked up. Right, because that is a different mechanism for acquiring and releasing this location than what the processor and the port connections do natively. But that's something that would have been relatively easy to do with something like process flow, because I get to decide when the acquire and when the release are going to happen in a sequence. It's up to me to figure that out, which is both good and bad, right? It's good in the sense that you get control over things. It's potentially bad in the sense that you have to be in control of more things. Does that make sense? So with that client's model, the way that I solved it was actually just putting queues in, like a buffer in front of and after every processor. And I limited the content of those buffers to 1, so that they could always have one piece of work waiting while they're doing something, and one piece of work waiting to be picked up and taken to the next location, but it didn't impede their ability to work on something. Because I needed, like, this connection from processor to processor wouldn't work for that example because of the blocking mechanism that happens when you have downstream availability that's blocked, and now you have to wait here. And that actually puts the processor into this blocked state where it's saying, hey, I could work on something, but my downstream locations are busy, so I can't send anything, which means I can't receive anything. So we're blocked. Okay, does that make sense? Anyone have any questions there? All right, so in this next section, we're gonna see another way that you might approach the integration between process flow events and object-based events. So in the last example that we did, process flow was still mostly in charge of everything. And 3D objects were only used as a way to visualize parts of the process, so that we could actually see like 3D objects moving around and doing stuff. But the objects themselves weren't really that involved in what was going on. And like I mentioned too, that's a fine approach sometimes, but there are other times when there are things that the objects already know how to do that it would be nice to be able to take advantage of. And there's going to be times when the objects don't know how to do what you want to do, and it's going to make sense to use process flow. And so how do we combine this idea where there are going to be times when we want to have process flow logic happening in conjunction with or in support of object-based logic that's a little bit more complex than just putting something inside of a queue? So to support this kind of an approach, we developed a set of activities that are called event listing. They create an approach that's called event listing. Now, remember that everything in FlexSim is based on the execution of events. And the idea behind event listing is to allow tokens in process flow to be affected by events that are happening someplace else in your model. So that you can say that there are things that happen in your model that are contingent upon other events having happened. And so there are 2 ways that we use event listing. We can either cause a token to be delayed until some event takes place. So the token would go to the wait for event activity, and its flow would be suspended until the event that you're waiting for actually happens. Or you can cause a token to be created after a particular event takes place. So in each instance, with wait for event and the event triggered source activity, we are saying that something happens because we are waiting for something else to happen. So like, for example, the event triggered source would say that, you know, your model's executing a bunch of events, whatever they might be. And then when the event that the event triggered source is tuned to, when that event happens, then a token gets created, which then allows you to execute whatever process flow activities you want as a result of that other event having happened. Okay. So let's take a look first at this idea of the event triggered source. The event triggered source, the properties for it can look a little bit intimidating at first. So I created this diagram to kind of try to explain what each piece of the event triggered source does. So again, the main thing to remember is that it creates a token in response to some other event that happens in your model. So rather than creating a token based on a time or some kind of a schedule, it creates a token because something else happened, some other event happened. So the first thing when using the event triggered source that you need to set up is the object that you want to listen to and the event on that object. And these 2 things taken together will be the event that causes the token to be created. So like in this case, we're saying listen to Q1, and during the on entry event, a token will be generated by this activity. Now, there are a number of other things that we can do once the token is created. And we'll look at some examples here. Like, for example, a very common thing is that you want to capture data that is reported by the event that you're listening to and save it onto a token. And so this label assignment matching value area gives you the ability to do that. And we'll take a look at that in practice. So let's actually take a look at this in a model, because again, I think this is a little bit easier to understand with the model. So we'll start with what we've got here, just a simple couple of objects, and I'll just modify it a little bit. So we'll say that we've got another queue here, and then that'll go to another processor. And then in my process flow, actually, let's go ahead and put that sync back in there as well, just for fun. So we've got this whole potential process of things that are being controlled by the objects, right? We've got a source object that's creating flow items. We've got queues, processors. Maybe you've got an operator in here as well. Maybe you've got something like this operator. Oof, there we go. Needs to transport things into Q2, right? So if we let this run, it works pretty much the way that you would expect. Flow items arrive, and then when their process is done, the operator is going to go pick them up and put them in the queue. And so we have all of these events executing in the model. And if we open the event list, we can see those events as they're scheduled to happen. So the first activity that I want to show you here is the event triggered source. So if I come back to my process flow and find the event triggered source in my library, I'm going to drag this out. And remember that the job of the event triggered source is to create a token, but it creates a token not on a timed basis, like the inter-arrival, the schedule, or the date time source. Those all create tokens based on time. The event triggered source creates a token as a response to another event. So notice that the event triggered source has that exclamation point on it that you might recognize from the acquire activity, which means that this activity needs some configuration before it will work. In fact, if I don't resolve this exclamation point, if I were to hit reset, it's going to give me an error right off the bat that says, hey, you haven't defined the event that you want to listen for on this source activity. And so it's going to give that error right off the bat because it says, I need to know what I'm listening for. So if we take the exclamation point, turn it into the eyedropper, and let's say that we're going to listen to Q2, and we're going to say that we will listen for the on entry event. And now if I let my model run, whenever a flow item is placed in Q2, that generates a token. So keep an eye on the operator. Whenever a flow item is dropped off in the queue, that creates a token. And so even though those flow items, again, are going out to the sink, the tokens remain because the event triggered source heard the event on Q2 happen, and then it generated a token based on that. Okay, so this is sort of the reverse of what we saw with the create object activity, where tokens executing the create object activity caused the flow item to be created. But now flow items that execute certain events in the model are causing tokens to be created. An important aspect of using the event listing capabilities of process flow is that there is data that is reported by the event that you're listening to. So down below the object and the event that we're listening for, there is a section devoted to this event data. And so the event data listed in this column says that when the on entry event happens, we have access to the information that refers to the entering item or the item that actually caused the on entry event, and also the input port number that item arrived to this object on. So when we execute the onEntry event to Q2, we know what item arrived into Q2, and we know what input port it used in order to arrive at Q2. And so this information is reported by the event. And this section of the table over here allows us to decide if there's something that we want to do with that information. One of the most common things that's done is to perform an operation that does an assignment. So if we say that we want to perform an assignment, that means that we can designate a label name where this data will be assigned to. And this is a label that is on the token. So if I were to say that I want to save the data for the entering item onto the token into a label, I'll call this, I'll just call it box. It doesn't matter what you name it. It can be whatever you want. There we go. So this would mean that the item that enters into Q2 will be assigned to the label on the token called box. So if we reset and run this now, when that first flow item arrives, if I take a look at that token, it now has a label on it called box that refers to the flow item that is inside processor 2 now, but that reference was established when it arrived into the queue. And so now this token again has that reference to the flow item, just like what we saw when we did create object, where we said that the item is being written to the token, but now that's being done from, like I said, the other direction, where the token is created because the item did something rather than the item being created because the token did something. Okay, anyone have any questions on that so far? So from here, we start to get access to all the things that we would normally do with a set of activities. Like you could do maybe a change visual, where you could say that when the flow item arrives into the queue, we're going to set the object color. We'll just let it be something random. But now instead of doing it to a reference to an item on the token, I have a different label name. So I'm going to say that this is found, the object that we're referring to is found in the box label. So now when flow items arrive, we will create the token and we will also change the color so that every time something arrives into Q2, it goes from a brown box to a randomly colored box. But again, that's being handled from the process flow side because the token is created as a response to the arrival. Then the very next activity says to change the color. Okay, so this is a fairly simple example, hopefully just kind of introducing this idea where tokens get created because flow items do something, and then we can allow process flow to execute whatever behavior we want after that point. And so to kind of help illustrate this again, I'm going to set up an example using this model that admittedly is a little bit contrived, but it gives me a way to introduce a couple of ideas in a simple environment. So take this more as like a concept demonstration rather than something that you might actually do, right? So let's say that we get rid of this thing and we've got a queue over here. And this processor, we're going to say that it has a setup time of 3 seconds, a process time of 10 seconds. But maybe I also want this processor to have some other kind of a delay that represents like a cleanup time. So the flow item arrives, it gets set up, it gets processed, but then we need to keep the flow item in the processor while we clean it to trigger like a cleaning time that needs to happen on processor 2. Well, as you notice, the processor object doesn't have a third kind of delay. It has a setup time, as a process time, but it doesn't have another kind of a delay that represents a cleaning time. So this might be an example, a simple example, where process flow might be used to enhance the behavior of the processor. Now, I took the sync away because I don't want the processor to just send away the flow item when it's done. I want process flow to be able to do something, which means I need the item to stay in the processor and to keep other flow items out while the while my new cleaning time is happening. So in order to do that, I need a token, and I'm going to create one using the event triggered source. I'm going to keep this part the same, where we say we listen to the arrival into Q2. We keep the flow item being assigned to the box label on the token. But now I'm going to add in another activity. I'm going to add in an activity called, well, actually, first of all, let me demonstrate this by putting in a delay, right? Because this is one of the things that's really important about event listing, where we think about what happens when a processor delay time is competing with a process flow delay time. So let's say that this delay represents cleaning. Now watch what happens here when we get our first flow item into the processor. Okay, I'm just going to pause it right here. Let's look at the event list. Notice that the processor has an event that it is waiting to execute called the end of the setup time, because right now we're in the middle of our setup event. And at the same time, we have a token in process flow that is trying to do the cleaning process. Token ID 1, it's this guy right here, is trying to do a process flow event for this cleaning time. So the token is actually running its delay simultaneously with the delay of the flow item. Because remember, when a flow item enters an object, it immediately just begins the regular event system of the object. The object doesn't know that it needs to wait until some other thing happens before it can do something. It just starts executing all of its events. As soon as the flow item arrives, it just starts executing events. But if I want this delay to happen after the processor finishes its events, then this is a reason why you might include something like wait for event. So I'll drop them between each other. And again, notice the wait for event wants to know what event we're listening for. And so we're going to say that we're going to listen to the processor, and we're going to listen to the send to port event. Now you might be asking yourself, why are we listening to send to port? We listen to send to port here because that is the last event that the processor has scheduled for a flow item if it doesn't have any output ports. So if you are listening to a processor and you potentially want to move that flow item out of the processor, it is safer to listen to send to port instead of process finish. So that's why I didn't even do process finish, because most of the time you're going to want to listen to send to port, because what we're basically saying here is that we want the token to do something only after the processor is done doing things. And so the thing that we're listening for here is send to port, because once my cleaning delay is over, I want to be able to move my flow item. We're going to move box into Q3.
Is send to port logically before exit?
Yes. Yep. Send to port happens first because send to port figures out where you're going. And on exit, it means that the flow item has actually left.
Okay.
Yep. So in this case, we're listening to send to port because that's after the process time, that's after the setup time. And it's the time when the processor essentially says, this flow item is now free to go because I've done everything that I want to do for it. I have no more events that I want to do for this object. So it's now essentially released in the sense that it's free to leave. And since one of the things I'm going to do after that wait for event is cause the object to move, it is better to listen to send to port in that case because that's safer. There are some weird errors and some weird behaviors that can come up if you listen to an event and subsequently move that flow item out of its object while that object still thinks that it has events to do on behalf of that flow item. So this is just safer. So watch what happens now with this little setup where the flow items will enter into the queue. We create our token. And now notice that the token, I'm just going to slow it down, that the token is waiting at wait for event, because it's saying I'm waiting for this event to happen. I'm waiting for send to port to happen, which won't happen until we get to the end of the process, which then releases the token to the cleaning delay. And then when that cleaning delay is done, we'll cause the box to be moved into Q3, which then makes the processor available again, which allows the next flow item to enter into the queue, or excuse me, enter into the processor. So again, we can see that token waiting for something to happen. We're saying you got to wait for the processor to be finished with everything. We're waiting for send to port. And only then is the token released to the cleaning delay. And then only then is the flow item allowed to go to Q3. Okay, so far so good?
I got a question. So
Yeah.
so there's actually no port connection from processor 2 to Q3. So if you wanted to have an operator move from processor 2 to Q3, how would you do that?
We'll talk about that in the next chapter.
Perfect.
Yeah, it's good. Good natural question to ask at this stage, but I have an entire chapter just on that idea. So yeah, we'll talk about that. Okay. Now there's something interesting that's about to happen, and it has to do with the way the wait for event activity works. And it's an important thing to talk about. So just know that what we're about to see is not an error, it's a feature. And we'll talk about how to use different properties of the wait for event activity to give us some different kinds of behaviors. So this flow item that just arrived, it's in the wait for event. And so it did its setup time, it's doing its processing time. And at that same time, another flow item enters into the queue, which creates a token that is also now waiting for an event. So we have two tokens that are waiting for the same event. If you have two tokens present in a wait for event activity, that means that they are both waiting for processor 2 to do send to port. So that means when that event does happen, the flow item that was in the processor got moved, but now look what's happening here is that we have a delay that's going on at the same time as the processor delay. And before the processor can finish its delay, the purple box actually got moved out of the queue. And so we have a little bit of strange behavior going on now, where if there are multiple tokens that are waiting for the same event, they can cause some weird behavior to happen to their flow items. Like there was a flow item that moved out of the queue without ever going to the processor. I don't know if you noticed that. But like right here, same thing again. Both of those tokens now are doing the delay, and they both might end up getting moved into the queue in the wrong order, in the wrong sequence. Okay, so the reason why that's happening is because if multiple tokens are waiting for the same event, the wait for event activity behaves like a traffic light at an intersection. The light turns green and everyone is allowed to continue. Right? So it doesn't matter when you got to the wait for event or when you get to the intersection. If you get there like 2 seconds before the light goes from red to green, then the light is green, you get to continue. Right? And so the wait for event has this capability on purpose so that if there are multiple tokens that could potentially reach in a certain point of their flow where flow needs to be temporarily suspended and then continued, the default functionality without any other settings of the wait for event basically mean that you're collecting a kind of a batch, and that batch is released as a result of the event that you're listening to. And it doesn't matter when you arrive, as long as you arrive before the execution of the event, then you are going to be part of that released batch of things that moves on to the next set of activities after the wait for event. Now, in this model, that actually causes us some problems because it allows the boxes to be moved out of the queue before they get processed potentially, or they might get moved out of the processor before they're done being processed. So there are additional controls built into the wait for event that allow us to create like a filtering mechanism on what tokens are actually allowed to leave the wait for event. And we handle that with this label matching and assignment table, similar to what we saw with the event triggered source, where we are allowed to listen for particular event data and then only release tokens if the operation says that we are going to do a match. So in this case, if I say that the box flow item, the data in the box flow item has to be a match for the released item on the processor, then only will the token be released from this activity. So remember that each token has a reference to a flow item on it. And so if I say that the flow item reference has to match the item released by the processor, or has to match the item that caused the send to port event to happen, then only that token is released from wait for event. So the first couple of flow items, it doesn't really look too much different because there's nothing else waiting in the queue. But now when we get to the point where we have, like right here, where we had two tokens waiting for the same event, and we just barely missed it. Let me just kind of get back to that point. So right about, oh, I stepped past it again. My bad. All right, so now we've got that red box in the processor. We're about to get that purple box into the queue. And so right here, both of these tokens are waiting for the same event, but now rather than releasing both of these tokens to the next activity, we're going to say that we only release the token whose box is a match for the released item that belongs to processor 2. So now only one token will go to the queue, and now the purple box will also wait for the event, but now it's waiting for the event that is caused by its flow item instead of any flow item. Okay, does that make sense? Anyone have any questions there?
What would the other options in the operation column mean when we say match value or insert at front?
Yeah, good question. So like assignment, we already talked about, right? Where it assigns the event data to a label that you specify. But matching a value is different from doing a regular match. And matching a value means that if the event data that's returned by the listener is a numeric value, like if it's a number, then you can match the value of the event data with some other value. So kind of the best way to illustrate that really is at this event triggered source, we can do that with the input port, because the input port event data is a numeric value. And so if we said that the operation that we want to do here is a match value, and let's say that we put in the number 2. So that means that the input port number has to match the value of 2. And if that is true, then we will create a token on the event triggered source. So because there is no second input port to Q2, then we're not creating tokens, because this is saying that, well, if the input port that arrived or that was used to arrive to Q2 is not number 2, then we're not going to create a token. And so this would create no tokens ever, because there's never a second input port that arrives into Q2. And so it's a similar idea on the wait for event, where you can say that there is a value that you want to match, instead of saying that this label value has to match this thing. You could say that there's a value that has to be matched instead. And then insert at front of is a way of building a label array, where instead of assigning a value, you're taking a value and inserting it into the same label. So you have like 2 or more values in the same label instead of just one singular value. The idea of label arrays isn't something that we've talked about yet, but it should come up later on in the week. But that's just what that means. Insert at front of means that we're going to make an array. instead of a single value in the label. And I think I talked about that stuff in these slides. Yeah. So you can refer to these for the wait for event, where it outlines what this section does and what the match and match value insert in front of and what those kinds of things do.
Got it.
So in this little example, again, the idea is to kind of hybridize the model where there are things that the objects are doing, and then there's this little piece that process flow is in charge of, where I'm just saying, hey, I just want you to be able to execute a cleaning time for me. In fact, you might even like put this in a container just for like documentation purposes. Or you might call this like processor to cleaning logic. Right, and so it's just this one little piece set of activities that's supplementing something that the objects are already doing, right? Improving the behavior of the model by adding in a little bit of process flow to supplement what the object events are doing. And so using event listing is very handy for that, because it allows us to say that process flows events are contingent upon events that happen someplace else, like out here. Okay, so how does this apply then to the model that we've been building? So if we were to apply this hybridized notion to our model, maybe instead of letting the delay times being handled by process flow events, maybe we want to use processors. Maybe there's something about the way processors do things that we want to take advantage of. We could add in processor objects here. That represent the processes that we need to do for inspection, cutting, curing, and polishing. I'm going to make 3 processors over here because we've got 3 curing slots that we need to account for. And I'm just going to make these a little bit smaller just so that it's not quite so much going on. And maybe this processor 1, maybe we call this inspection. Whoops. Now we call this one painting. We call this curing 1, curing 2, curing 3, cutting, and polishing. And if we like the processors to handle things like the delay times, maybe we also like the fact that we can use port connections to manage the availability of these processors. And if we're using port connections to manage the availability of these processors, that means that I don't need resources anymore, because the whole point of a resource is to help us manage availability, which is something that the port connections can also do. And if we like the way that the port connections manage the availability, then there's no reason to use a resource, which means that I don't need acquire and release, which means I also don't need the delay, because the processors can do all that. So what I'm left with now is a move object that's going to move things into this queue. Now, before I allow the next move object to happen, let me just pull that one out and delete everything else. Before I do this next move object, I need to know when the processor is finished. when the processor is done working with the flow item. So that means I could do that with a wait for event. And so instead of having the acquire, the release, and the resource and the delay, I can say, well, let's just let the processor do it. And let's listen for when the processor is done working with the flow item. And so we will listen for the send to port event of the inspection. And we will say that we can't move the item unless it matches the item that was processed by the processor. So in each of these blocks, then I can simplify things by saying, let's have wait for event after every move. So here we'll listen for paintings send to port. And we will also say that the item needs to be a match. And so here I can say, let's get rid of everything except for the move objects. Let's bring in our wait for event. Now, curing is actually a slightly different case, so we'll come back to that one in a minute. But I'm just going to do everything else. I'm going to use the double click menu just to hopefully make this go a little bit faster. And we'll say, listen to cutting process or cutting send to port. And let's make sure that we match our items. Oops, wrong thing. Listen to inspection, send to port, and then match the items. If I'm going too fast through this, just let me know. I'll slow down. But it's just replicating the same set of clicks over and over again. So hopefully it's not too hard to follow. And remember, that's the control drag feature that we talked about earlier. Again, just making sure we match up our items so that we don't release a bunch of things waiting in queues. Again, curing is a little bit of a different case, so we'll leave that and come back to it in a second. I'll just bring out the wait for event. And finally, listen to inspection again, send a port, and match the items. Okay, so the reason why curing is a special case, and I wanted to save that one for last, is because for all of the other processes, we just needed to listen to one processor, right? You listen to inspection, painting, polishing, cutting. But with curing, there are 3 processors that you could potentially have to listen to, because there are 3 curing slots, right? We said that there are 3 things that could cure at the same time. So if we move to this event listening approach, that means that we would need individual processors for each of the curing slots that could be used by the flow items. Now that means that when we're waiting for an event, we need a way to listen to multiple objects at the same time. We don't want to just listen to only curing 1 or only curing 2. We want to potentially listen to all of them. And so this is where object groups can be useful. We mentioned object groups yesterday in conjunction with our experiments, but object groups also help us simplify the active event listening, where I can shift select a group of objects like this and turn them into a formal object group, where I'll say that they are going to be added to a new group. And I'll call this my curing group. And notice that we have curing objects 1, 2, 3 in this group. And that means when I come back to my wait for event for curing, I'm going to shift click in this empty grid space to turn off the red halo here. And so now if I come back to my wait for event where I have my exclamation point, if I go to one of the curing objects, it gives me the choice. Well, do you want to listen to this particular object, or do you want to listen to the group that it's a member of? So that's kind of nice. And again, this is one of the reasons why I like including the word group in the group name, just again to make sure I differentiate, hey, we're talking about a group here. So if I go to the curing group, it says these are the events that are shared by the members of the curing group. So in this case, I'll say, yeah, let's listen to send a port of any member of the curing group, and also match those items to make sure that only the item that actually causes the event is the one that gets moved. And then over here, I'll do the same thing. We say, let's listen to the group, send a port. And so now my flow has gotten a lot more simplified, right? Because I'm turning some of the control over the model back over to the objects. And so now when we run this, the processors are executing the processing time. The queue in the processor, the queue before the processors is figuring out whether or not the processor is available. So that's removing the need for the resource. And now the only thing that process flow is doing for me is managing the flow from station to station, which is something that process flow is very good at doing, because it allows me to manage the flow in a much more visual way. So I don't have to have port connections from every station to every queue, and then have some kind of like a logical algorithm that tries to figure out, well, if you're at this station and you're this type, then you go to this next station. But if you're this other type, at this other station, you go to this other place. And so I can still maintain my my linear approach to managing the flows and visualizing the tokens representing the flow items going through the system. But I'm letting the objects, the processors, do some things that they're good at doing by letting them manage the delay times and their availability. So this is much more of a hybrid model now, because process flow isn't in charge of everything, but it's only in charge of something that it's good at doing. Does that make sense? Anyone have any questions on that? Okay. So like I said at the beginning, it's just another approach to managing your model, right? If you like the fact that process flow gives you a lot of control over everything, and you want to take control of your model from start to finish using process flow, and then only using the objects to visualize things, kind of like to supplement what you did in process flow, that's great. There's a lot of people that build models that way, and it's a good approach. But if there are things that you know that the objects do and you want to be able to take advantage of that, this method might be a good method to take also. And there are other approaches that we may take to integrate 3D and process flow, and we're gonna have a bunch of models that introduce some other more particular approaches in addition to these that we've talked about already. But these are the two primary ways of thinking about the process flow versus object integration, is to think about kind of who's in charge of what aspect of the model. Are there things that the object should be in charge of, or are there things that process flow should be in charge of? And you know, kind of all those things that we've been talking about. Okay, so rather than jump right into the next chapter, how about we take our break a little bit early again today? We'll do our lunch break now, and we'll come back in an hour. And when we come back, we're going to jump into taking a closer look at task sequences and the control of task executor objects.
Sounds good.
See you in an hour.
All right, we'll see you guys back in an hour. Okay, well, welcome back from break. In this next section, we're going to take a little bit of a deep dive on something that we just sort of glossed over when we introduced talking about the objects a little bit earlier. And that is the idea of a task sequence. And in fact, this is something we didn't even really give a name to it. We mostly just kind of let the standard object behavior handle the stuff behind the scenes about creating and executing these task sequences. And essentially what a task sequence is that it is the mechanism that we use to control a task executor object. So in any of our models where we asked an operator to do something on our behalf, we were creating a task sequence, which is made up of a sequence, like the name suggests, of individual instructions or tasks that tells the operator or the task executor object exactly what to do and in what order to do it. So for example, if you're over here at a pretty simple model where I just put this together with the connections and using the default options, but then on the queue say that I want to use transport, the act of clicking that use transport checkbox means that the queue is going to create a task sequence, and it's going to give that task sequence to whatever object is referenced in the use transport field of its properties. And that is what tells the operator exactly what to do. So this act of carrying a box from the queue to the processor is a task sequence that is made up of several steps. It says that we are going to travel to the queue. We are going to load the flow item that we find there. We're going to travel to the destination, which in this case is processor 1, and then we will unload the flow item to the processor. And then if there's nothing else to do, the operator just stands and waits for further instructions. So that's why the operator doesn't go back to the queue, because that's too big of an assumption for us to make in the baseline task sequence. We don't include an additional travel step that says after you get done unloading, go back to the queue, because there might be other things that you want the operator to do immediately upon unloading. And so since we can't know that, we don't assume that that's what you want to have happen. And so we just let the unload part of the task sequence be the last step that the operator executes. But remember that we did talk about a trigger option on the operator, where you could say that when the resource becomes available, right, using this on resource available trigger, you could add an action to that trigger that says that you're going to travel to a home location or to a home XYZ coordinate. And so this happens after the task executor finishes a task sequence. So after all the tasks of a given task sequence are done, we evaluate this trigger and we say that this is your destination to travel to, whatever is referenced by your center port. And this is the condition under which you will travel to that home destination, which at this point says that the resource, which is the operator, number of task sequences, or where it says task sequence.length, is equal to 0. So if you have no task sequences waiting to be done, then that means you can go home. So here that means that as soon as he becomes available, he walks over to the queue, and then as soon as he goes back to the process or drops something off the processor, he goes back to the queue and waits for instructions there. Now, there's one other thing here to note about the creation and execution of this task sequence is I want you to know, like right here, why isn't the operator picking up the next box? Right? He's standing at the queue. He's not apparently doing anything. Why not pick up the next box? Why does he only do it at that point? Anyone want to guess?
The processor is busy with the previous box.
Exactly. Yeah. So again, this is the assumption that we made about the way task sequences are created, that says that even though the operator is available, the processor is not, because its input port is closed. And so the assumption here is that if the processor is busy, we don't even create the task sequence yet that says to load the next flow item and bring it to the processor, because this processor might not be the only destination, right? There might be other places that you might have to go. So we don't really know where these flow items want to go yet. And so we say that we don't try to load the flow item until a flow item has actually been sent essentially to a destination. And then the operator is going to say, okay, I know where you're going. Now I can pick you up and carry you to the destination. Right, so there's no like anticipation here because the events of the queue still need to check to find an available downstream location and only creates the task sequence when that downstream location becomes available. Okay, so task sequences that we've seen so far are created as part of the order of execution of events that are associated with an object. And we've seen a few of these in places already where we encounter the sequence of events that says, hey, at this point, we need an operator for setup, or maybe at this point, we need an operator for processing. And we choose our operator by using this like pick operator field. Or maybe we get to a point where we need to use transport. And so the same thing will happen where we say, hey, this task sequence is created at this point and is given to this object, whether that be a dispatcher or a task executor directly. It's the same kind of an idea. But these events are what create the task sequence and then in turn tell the operator what to do. Now, one thing that we haven't seen very much of yet is what happens if we have multiple objects that are requesting the same task executor, and how are those task sequences going to be handled? How does the operator know what task sequences to execute first? Well, every task executor has a, we call it a node, but it's basically a mechanism that is in the data structure of the task executor that stores task sequences that are waiting to be executed. And we call this the task sequence queue. And so every operator has this little task sequence queue inside of itself, where it looks at all of the available task sequences that are requesting that operator. And so every time a request is made, that request will go into the task sequence queue. And if the task executor is available, it'll get moved up into another node that we call the active task sequence. And the active task sequence is the thing that the operator is doing right now. And the task sequence queue are all of the other task sequences, if any, that are waiting their turn on the task executor. And so the task sequences that go into the task sequence queue are elevated to the active task when the operator becomes available. And the sequence by which the operator works through the task sequence queue is to sort them by a priority value. Now, by default, all task sequences in FlexSim have the same priority level. We leave it up to you to decide what task sequences are considered more important than others. And so if all of the task sequences that the operator has in their task sequence queue are the same, then the task sequences are processed first come, first served. But if you change the priority value such that the priority value is higher, then the higher the value associated with the priority, then the more important the task sequence is, and the higher priority task in the task sequence queue will be elevated to the active task next, whatever is the highest priority. So anywhere where you can assign a task sequence, you'll notice this little priority field. It's like if we take a look back at our model and look at our queue properties, you can see that there is this priority field that says that it's currently set to 0. So if there are multiple task sequences competing for the same operator, then those task sequences are ordered according to their priority. And the higher the value, the higher the numeric value, the higher the priority, right? So a priority value of 1 would be 1 point higher than a 0. A 2 would be 1 point higher than a 1 and 2 points higher than a 0. You know what I mean? So it's just purely numerically sorted. So try not to like attach any like human meaning to like saying, oh, this is priority number 1. Does that mean that it's the highest priority? No, it just means that it's the next highest priority, 1 point higher than 0. Okay, now another option that we have available to us to manage the task sequence queue of an operator is this notion of preemption. And preemption means that some task sequences that are very high priority have the ability to preempt a task executor away from what they are currently doing. So let me just show you a quick example of that. So say this priority 0, good. And then I'm just gonna set up another couple of objects over here, just a source and a sink. And I'm going to say that the source also needs to use transport. The tasks that are created here, though, are priority 1, and they are going to allow the operator to be preempted. Okay, so now as we run, we are waiting for something to do. And so the source needed something transported first, so it just went ahead and did it. Now, notice there that the operator was on his way to Q1, but he got preempted over to the source to pick up a flow item. And because the tasks created by source 2 are more important than the tasks created by Q1, if there is something to do at the source, then the operator will do that first. So right now, there are a lot of things that the source is asking to be transported. And when we drop that off, there's something there again that needs to be transported. And right here, when we drop off that flow item, the operator is now on his way to Q1. Oh, and then he got diverted back over to source 2 because he got preempted away from the task sequence that he wanted to go do, which was to get something out of this queue. And again, that only happens because the priority value for this task sequence is set to a 1, and the preemption rule says that we are preempting the operator. So now the operator looks like he's going to get a chance to start that task sequence. Oh, and then right before he got there, he got diverted away again. And so the task sequence that got preempted, that was going to pick up that first box in the queue, that gets put back into the task sequence queue so that the operator could potentially finish it when he gets done with whatever preempted it. And that's what the preempt only rule says. So here it looks like he's going to make it. Yay, he got to pick up that box. But that doesn't mean that he's safe. Because while he's carrying that box, if source 2 were to create something, he would get diverted over again to source 2. So it looks like he's going to be able to get something else out of Q1 now. Oh, but only if the processor finishes. So he's just waiting. He's truly idle for once. And now he picks up that next box out of Q1. We'll see if he makes it to the processor. Okay, cool. He made it. And now source 2 needs him. So he's going to go over and get the thing out of source 2.
If you didn't make it to the processor, does the box go back to the queue? Or
No, it just stays with the operator.
Oh, okay.
Because we didn't want to assume what to do with the flow item. So if the operator actually did load the flow item before he gets preempted, then he just holds on to it and waits to try to drop that box off at a later time.
Okay.
Now, if there's something that you want to do, like maybe he puts the box down on the ground or something, or I don't know, something along those lines. There are triggers and options that you can use to do that, but we generally leave that in your hands to figure out, because invariably any kind of assumption we make like that would be wrong for somebody. So we just say, yeah, operator hangs on to it. It's up to you to decide what happens after that.
Okay.
Okay, now preempt only is probably the most common option here. These other two options where it says preempt and abort active, preempt and abort all, those give us some options about how to handle the task sequence queue when a preemption actually takes place. Preempt and abort active means that the active task actually gets aborted so that it never gets finished. So if you're doing something like right now, he's carrying a box, let's say that like right there, he just got preempted, right? So he's carrying that box. So he's going to drop off the box that the source had first because that was higher priority. And now he's going to go drop off the other one because we're currently set to preempt only. But if that had happened while it said preempt and abort active, then he would never drop off this box. The task sequence associated with that box would have been destroyed. And again, it would be up to you to decide what to do with that box when the task sequence gets destroyed off of the task executed. Because again, too big of an assumption for us to make. So we leave it to you to figure out how to handle that if it's something that comes up. Now, kind of closely related to that is this idea of preempting and aborting all. Preempt and abort all means that if there are multiple task sequences in your task sequence queue at the time of preemption, then you will do the task sequence that you were preempted to do, and then you will delete every task sequence out of your task sequence queue. And again, it would be up to you to decide how to handle any flow items that like get abandoned, so to speak, with no task sequence that says to move them or to do anything with them. Because if it gets aborted, if they all get aborted, then all those task sequences are gone. And again, that's why these are options that you can choose about which of these mechanisms to handle the task sequence queue you want to use, whether you don't preempt at all, where everything just is executed according to their priority value, or whether you want to employ some sort of preemption rule about how more important task sequences should influence the task sequence queue. Hey, does that make sense? Anyone have any questions there so far?
Are we going to get into how to represent preemption in process flow? Is it
Yes.
a little bit different? All right, cool.
It's the same mechanism, really. But process flow does give you more controls over what to do with preemption style events. Because in process flow, you'll just naturally have more control over everything anyway.
Sweet.
All right, so this is pretty simple and straightforward. But one of the challenges about working with task sequences is making sure that task sequences that originate from different objects happen in like the right order, in the right way. So I want to show you an example model. This is an example that is a fairly common kind of behavior, and in the past it was kind of difficult to really manage, and it's something that that bears a little bit of discussion, because I think it's something that happens often enough that it's good to talk about why things maybe don't work quite the way that you would expect. So you have access to this model as well. This is in the download materials that I sent out in the calendar invite in the examples and walkthroughs directory. And this is the task sequence demo that we're going to look at. Okay, so here is a simple little model where an operator is responsible for picking up flow items from the queue and carrying them to each of these processors in sequence. And while at the processor, we need the processor to be used during the processing time. So you can see here, we're saying use operator for process. So the operator needs to be utilized for the 10-second duration of the process. And then the operator also needs to pick up the flow item and carry it to the next processor. So with the first flow item, this looks like something that is fairly easy to consider, where our operator picks up the first flow item. He's now being utilized by the processor. He's not idle. He is like working the machine. And then when that process is done, he's going to walk back over to the end of the processor and pick up the flow item and carry it to the next processor. And so far, this looks pretty good, except now watch what happens right there. Why is he going back to Q1? Why did he not stay with the flow item that he was already engaged with? And why now is he running back to processor 10 to that other flow item? What's going on here? Would you say this is efficient behavior or is this chaotic?
Seems kind of chaotic.
A little chaotic, right? Yeah. But why is he doing this? Seems like a lot
He
of
doesn't
wasted
know not to.
movement, yes?
All the preemptions are equal.
Well, as it happens, we even said the priority of these processors is supposed to be higher. But even still, like that very first flow item that comes through, the flow item gets dropped off. And he immediately leaves that processor and goes back to the next flow item. And the reason for that has to do with the order of execution of events. So if you remember this, this is like the third time that I've shown this slide that talks about the order of execution of the events of an object, because it's an important idea to kind of refer back to. The need for an operator as part of a processing time doesn't happen until this part of the flow. And that's far enough down in the chain that if another task sequence was created before this task sequence, then those task sequences actually aren't competing with each other in the task sequence queue. And so the priority value doesn't even get evaluated. It doesn't even come into play. See, if we go back to this model and get to that point again. So we're getting to the point right here. And rather than run the model, I'm going to open up the event list again. And let's keep an eye on our events. So as we step forward, we can see that operator one's not in the event list yet. So we're getting, okay, so here's operator one. He's about to begin unloading the flow item to the processor. He still has possession of it. And this event is going to end at 74.25. We're at 70, or I guess we're at 74.26. And so this is, the clock is rounding up to 26. So we'll just step forward one more event. And so now we have dropped it off. And at this time, the processor is about to execute the end of the setup time. But the setup time is a 0 time. And so at this moment, the next task sequence in the task sequence queue has already become the active task. This operator, if you look at his state, says that he's already starting to travel empty, where he says that we are now traveling back to the queue to pick up our next flow item. And then this processor now says, hey, I'm waiting for an operator now because I'm about to do my processing time, but it's already too late because the task sequence to stay here and do this process wasn't created in time to compete with the task sequence that says come back to the queue and pick up the flow item. And so that's why the operator may occasionally abandon a flow item, because now he's just executing things in the sequence that those task sequences are given to him. Because the order of execution of events may not put the task sequence into the task sequence queue in time to allow the proper competition between the operator. And so this problem can be difficult to solve. And playing with priority values and preemption values is one way to go. It involves a bit of trial and error, and it can be a little bit annoying. The other option is to say, you know what, trying to make what I want to have happen actually happen using the default object capabilities is too much. It's too much work, or it's not easily done. So maybe I want to do it myself. And so that means that sometimes it may be necessary to create a custom task sequence that defines the sequence of steps of the task executor completely yourself from start to finish. So rather than allowing the default task sequence take control, maybe you need to do it yourself. And there's a lot of reasons why you might have to do it yourself, because it might be that the built-in task sequences of the object are insufficient. They may not happen at the right time. They may not execute the right steps, or it may just be difficult to coordinate across multiple objects. And so in any of those cases, when the built-in task sequences don't do what you need, building a customized task sequence may be the answer. So let's compare this version of the model with a customized task sequence that I built over here. So if we just watch the operator run for a second, then we'll talk about how we did this. So you can see that even though now there are flow items in the queue waiting, the operator is going to stay with this flow item all the way through until he drops it off at the sink before he considers picking up another flow item. Does this look more efficient? More like what we would expect an operator to do?
Yes.
Yeah, so this is an example of where trying to make the built-in task sequence do what we want may have been too difficult. And it might make sense to say, well, I know exactly what I want them to do, so let me define for them what I want them to do and how I want them to go about doing it. Because the nice thing about this customized task sequence is I don't have to worry about figuring out, like, that competition problem is, well, are we creating this task sequence at the right time? Or is it in the task sequence long enough that they can compete for the operator's time and attention? I can just define start to finish exactly the steps that I want the operator to do. And the way that I did that was by creating a process flow. And this process flow, the only thing that it's doing is it is controlling the behavior of the operator. So this is another good application for things like event listening. You can see I have an event triggered source here that lets me know when a flow item is ready to be transported. And then I create a task sequence, which is begun by this create TS activity. And all of these tokens now represent the task sequences in my task sequence queue. And I only allow a new task sequence to begin if I finish a task sequence. And so you can see that my task sequence is made up of a series of steps that say we're going to travel, we're going to load, we're going to travel, we're going to unload, and then we're going to wait for the processor to be finished with the flow item. And then we're going to travel, and then we're going to load, and then we're going to travel, and we're going to unload, and then we're going to wait for the second processor to finish with the flow item, and so on until we can finally drop something off to the sink and then finish the task sequence. Now, because of the way that I designed this task sequence, notice that I didn't need port connections here, because a task sequence like this will allow me to bypass the need for port connections, similarly to what we saw in our previous model example, where we only have to use port connections if they actually do something for us. I can use the task sequence to move the flow items around, which is part of the reason why we use port connections. And so I don't have to worry about any of these other flow items trying to use these processors, because my task sequence is limiting how many things my operator can do at once. Okay, any questions at all so far? Okay, so how do we actually use some of these task sequence based activities? Well, let's. This is again one of those things that to me is easier to show and talk about rather than just like throw a bunch of information at you. So we'll show it in context here. I'm going to start with a relatively simple model. Again, it's going to start with a source object, and we'll have a queue object, and we'll have a processor right there, and then we'll have a sink. We'll just connect all these up, and we have our operator. Actually, I'm going to disconnect from the queue to the processor. And so let's start learning how to use this custom task sequence capability by first trying to recreate the standard task sequence that the queue would create for us. And then we'll use that as a way to enhance what that task sequence knows how to do. Because like what we saw, the task sequence that we get for free by clicking use transport is fairly simple and limited. It really only knows how to do that's that one operation that says when the processor is ready to receive, begin transporting the flow item. So we're going to start by trying to recreate that action, and then we will enhance our customized task sequence so we can see the power of having a custom task sequence. So I'm going to start with a process flow. And if I want to create a custom task sequence, oftentimes the first thing that we need to concern ourselves with is to know when is it okay to begin the task sequence. And this is where event listing can be really useful, because if I use an event triggered source and say that I want to know when a flow item is ready to be released by the queue, I can say that I want to know when the send to port event happens, because if the send to port event of a queue happens, that means that there's a flow item ready to leave. So this is kind of similar to what we did before, and I'll document this as we go. I'll say this source is create token on flow item arrival. It's very wordy, but that's okay. And if I create a token, I want my token to be aware of the flow item that arrived into the queue, because the purpose of this process flow is to create a task sequence that will allow me to transport the flow item. So I need to know what flow item needs to be transported. So I'm going to do my operation that says that we're going to do an assignment, and I will call this label box, because I can call it whatever I want. Okay, so if we just leave it like that, right? If we say reset and run, then flow items that arrive into the queue stay in the queue, and they create tokens that reference the flow item that they're associated with. So here we've got 2 flow items now, which means we have 2 tokens, and they each reference a unique box. This one references the first box, and this one references the second box. This one references the third box, and so on. Okay, so now that I have a token, now I can actually do something with it. So let's start by introducing an activity out of the task sequence section of the library that says that we are going to create a task sequence. So we're going to say create task sequence. And we're going to say this is the task sequence to transport to processor 1. Okay, now when you create a task sequence, you have to specify to what task executor this task sequence will be assigned. So it assumes a label for resource, just because we had to have something in there. But if I want this task sequence to be created on my operator, I can just use the eyedropper and say, you are my operator that is going to do this task sequence that I'm calling transport to processor 1. Notice here that we have the priority value for this task sequence. We also have our preemption rule for the task sequence, just like what we saw with the regular object stuff. So it's all the same mechanism. And then we have a couple of labels that are going to be assigned to the token. So this label is going to keep track of the task sequence that this activity creates. So the task sequence, the actual task sequence, is going to be placed into the active task of the operator, and then it will be referenced by this label on the token. So the task sequence goes to the operator, but the task sequence has a reference that lives on the token so that we can work with the task sequence. So I would just leave this as the default. I haven't found a reason yet why you would change the name of this label, but it is generally what you'll want to just leave there, and we'll see why that's important in a little bit. There's also another label that will be assigned that will keep track of the task executor that was assigned in the first property. That might be useful if rather than explicitly assigning the task sequence to one operator, maybe there were like a group of operators that you wanted to try to assign it to, and this would keep track of the actual member that it was assigned to, as opposed to like the group. So this is just keeping track of the assigned task executor. This is keeping track of the task sequence that we're creating. And then this is the actual operator that we're assigning it to. So we're saying this task sequence is given to operator 1. We keep track of it with the task sequence. We also keep track of the label reference for the task executor here as well. Okay, so if we draw a connection between those two activities and hit reset and run, then our operator is actually being given task sequences right now. Notice that his state is being set to allocated idle because there is an active task sequence in his task sequence queue now that says that he is allocated, but we haven't given him any other instructions. All we've done so far is just said, hey, here's a task sequence. The task sequence doesn't have any steps to do yet, but all of these tokens represent task sequences that are being created on the operator. And so these tokens now visually represent the task sequence queue on the operator. All of those waiting task sequences that are waiting to do something. Okay, so let's give him an instruction. Let's tell him to travel over to this queue. So I'm going to go into the task sequence section of the library again. I'm going to say that I want my operator to travel. Now notice that there are 3 different ways to do travel. The simplest and most common way of telling a task executor to do a travel is to give him an object as a destination to travel to. You could also give the operator a XYZ coordinate as a travel destination. If you're working with an AGV on an AGV network, you may also give an AGV travel, which gives you more control over how that AGV traveler would interact with the path. Now, this is a little bit more complex. We're not going to worry about that at all this week because we're not going to deal with AGV systems at all. So we'll choose the most common travel type, which is to travel to an object. So I'm going to choose travel to object. I'm going to click it into my flow. And we're going to say that this travel represents traveling to Q1. Now, notice the properties for this travel. The first property wants to know what task sequence is this travel a part of? And the second property wants to know where are we going? So this reference to token.taskSequence is the same label that was created at create task sequence, where we keep track of the task sequence that we created on token.taskSequence. So by default, the way that you want to do this is to make sure that the first property to any task sequence based activity, any of the activities that come out of the task sequence section of the library, reference the task sequence that was created during create task sequence. Okay, so I just want to make sure that this input field matches this input field, because we're creating a task sequence, and then now we want to add this travel task to this task sequence. And the destination that we're going to set, I'm going to just use it. I'm just going to set it using the eyedropper, and we're going to say go to Q1.
So Regan, in that first step when we created the task sequence, we could have given that, we could have changed that name to something else.
For sure. Yeah.
Okay, if we want to call, okay, so then you would just have to use that specific name throughout then.
Right.
Okay.
Right. The big thing is whatever is written here, where it says assign to token.taskSequence, whatever you put in place of task sequence, like if you call it like my TS, then I would just have to make sure that here we're referencing that same label called my TS.
So I assume you could have several task sequences in the same model.
Yeah, definitely.
Okay.
Mm-hmm. Yeah. And you could be using multiple blocks of activities like this to create task sequences. And you might use different labels to say, well, this is this task sequence over here. This is this other task sequence over here. And we want to make sure that like when we do things like this travel task, we're saying, make this travel part of this particular task sequence, not some other task sequence. You know what I mean?
I do. Thank you.
Yeah, cool. So yeah, it doesn't matter what you put in here as long as they match. So I'm going to put this back to what it says by default. So that's task sequence. And this will also be task sequence. So again, let's just see what that looks like then. So if we hit reset and run now, the operator is idle. It's not doing anything. And when a flow item arrives, that's going to tell my operator to walk over to the queue. And there he goes. So he's at the queue, but now we don't know what else we have to do, right? So once he's there, we would like him to pick up this flow item, right? Now, right now on this token, we have a reference to the box that needs to be loaded. We have a reference to the task sequence that we're doing, and we have a reference to the operator that the task sequence was assigned to. So using this information, I can continue to build up my task sequence and give my operator things to do. So the next thing that I want to tell them to do is to do a load activity. And so the load task says that we can pick up a flow item and allow the operator to carry it. So if we say load, I'll say from Q1, because like the load here is from the point of view of the operator, right? The operator is loading things into himself, rather than unloading the queue, right? Unloading would mean that the operator is dropping something off. A load means that we're picking something up. And so the load here says that we are again making this load part of our task sequence. And the thing that we want to load is going to be the flow item that is referenced by this token. Now on the token, I don't have a label called item, but I have a label called box. So I'm going to use that instead. So here, instead of token.item, I'm going to say that the item that we're going to pick up is found by looking at the label called box on the token. And then the station that we're going to load from is just the item container. So wherever this object is found, that's where we're going to load it from. So again, this is one of those things that you'll probably never have to change because more often than not, you're just going to always load something from its container. It's kind of a weird thing that we even like give you access to that because I can't think of a reason why you would ever change it. But there it is. So again, if we just kind of see what this looks like. Now a flow item arrives, we walk over and now we've picked it up. And because the operator is idle, he puts his hands down just because that's part of the animations where he says that when I'm idle, I just stand still. And so since he's technically idle, he's just kind of standing there with his arms down. Now, if we actually give him somewhere to go, he'll look like he's carrying the box. So now I'm going to give him another travel. So again, this is going to be another just travel to an object. And this time I'm going to say travel to processor 1. This is part of my task sequence, and my destination is processor 1. And then once we get there, we want to unload our flow item. We'll call this unload to processor 1. And again, it's part of my task sequence, so I don't need to change that. The item that we're dropping off is the one that's referenced by token.box. And our destination is processor 1 again. So in the travel, we had to say that we're traveling to processor 1 so that we know that we get there. And then in the unload, we have to say that we're also dropping it off to processor 1. And then if I'm just trying to mimic the standard task sequence, at this point, I can bring in a task sequence that says to finish the task sequence. And under the properties for finish task sequence, again, we just have to make sure that this label matches this label so that the task sequence is properly complete. And then that should be the end of our little process here. So let's see how we did. So if we hit reset and run now, Again, the first flow item comes in, we pick it up, we carry it over to the processor. So far, so good. And so similar to the standard task sequence that the queue would create, the operator is now idle while we wait for further instructions. So second flow item, looking pretty good. Looks like it might be working. Watch what happens now, though, when there are two boxes. So we have one task sequence that is in progress. This is our active task. And we have one task in the task sequence queue. So one task waiting, which means that we need to carry this, this box out of the queue. Now, as soon as the task sequence is done, the operator immediately starts working on the next task sequence, even to the point of unloading two flow items into the same processor. So why is he doing this? Is this okay?
It seems like this, we don't have that restriction that the port has to be open for him to do that, right?
Yeah, exactly. Yeah, because we took the port connection out of the loop here, then there's nothing that says, hey, the processor is not available right now, so don't bring me any boxes until I'm done, right? And so because we took the port connection out of this, that means that it's up to me now to figure out whether or not this processor is available. So this is a good opportunity to use maybe a resource. So like if I were to, again, try to continue mimicking the standard task sequence, I could have a resource. And I'm going to say this resource represents processor one. So I'm just going to say resource, processor one. And now I need to say, well, okay, well, maybe we shouldn't create our task sequence until the processor is actually ready to receive. That's the way the standard task sequence does it. So what if we just, again, try to mimic that? So if we bring out an acquire activity, and I'm going to call this acquire, I'm going to say, is processor available? Right. So that's going to be the way that we know, okay, if the processor is available, then we'll be able to send it again. Now, how do we know when the processor becomes available, though? Like, we know that it's available at the very start of the model, but how do we know that the processor becomes available after the first flow item is processed? Well, we have to know when something actually leaves the processor. So this is another opportunity to use event listening, where we could use wait for event. And so I'm going to put in a wait for event right here. And I'm going to say that we are going to listen for the on exit event from the processor. Because if we listen for on exit, then we know that the processor is ready to receive after something leaves the processor. And so if something leaves the processor, then we know it's okay to release the processor. And now if we hit reset and run, step through the first couple. And so now when we have a couple of flow items in there, right, now we have our operator just waiting for further instructions, but now we have to wait for the processor to finish before we start the next task sequence. So here we've pretty much effectively recreated the standard task sequence with the acquisition of the resource taking the place of a port connection. And the reason why we had to use the resource to stand in for the port connection instead of making a port connection, because the port connection would have just taken the flow item away to the processor without giving me a chance to create the task sequence. So I needed to disconnect them in this way so that I could have enough time to create my task sequence and give the instructions to the operator. All right, so right about now, you're probably wondering, okay, this is cool and all, but why? Right? If I can do this exact same thing with the port connection, why would I ever do this? Well, remember I said at the beginning that the reason why we're doing this is to create a task sequence that behaves like the standard task sequence so that we can get familiar with these activities. But one of the cool things that it also does give us is now we have some neat abilities to change the way this task sequence works to potentially change the behavior into something more customized. Because remember, the next task sequence isn't allowed to start until the processor actually has the flow item leave, right? It's not until this point that the operator can begin carrying the next flow item. But wouldn't it be nice if the operator could anticipate that there is another flow item that needs to be dropped off at this processor, and maybe he could start carrying the next flow item to the processor before the processor actually gets finished? Because there's all this time during the processing time where we're just waiting around, right? What if during this time he was already traveling back to the queue, loading the next flow item and on his way back to the processor? That's something that the standard task sequence can't do, but it's something that I can do with my custom task sequence. Like, for example, I could say, well, maybe I don't care if the processor is available until after I've traveled to the processor. So if I just move where the acquire happens, right? Now I can say that I pick up my first box, pick up my second box. And now when I pick up my third box and drop it off, I'm already on my way back, loading the next flow item, walking to the processor, and now I can just wait. And then I can drop it off. So my task sequence allows me to change the way things are done. It allows me to define my own behaviors. I could give him intermediary steps that he needs to take while on the way. Like if there's like some, like kind of like a check-in where he like picks up the box and takes it to a terminal, scans it, and then brings it to the processor. I could add in those extra steps in the task sequence as well. I can change when it's okay to unload, because now I have an acquire activity that is gatekeeping the unload part, where I can say, well, I'm just going to hang out with my flow item. I know it's going to be done soon. And then I can drop it off when the processor actually does become available. All stuff that I can't do with the standard task sequence, but if I recreate it using my custom task sequence tools, I get a little bit more control and the ability to customize what the operator is going to do. Okay, any questions at all? So let's again give you guys an exercise where you can try some of this stuff out. Oh shoot, there's one other thing I wanted to show you. Dang it. All right, so there's one other activity that I forgot that I want to show you at this point before I give you guys a chance to try task sequences out on your own. The batch activity is kind of a weirdly abstract activity. You can kind of think of the batch activity as both a combiner in join mode and a separator in split mode at the same time. Because what the batch allows you to do is it allows you to specify a quantity of tokens that you want to collect into a batch, and then another number of tokens that you want to release from the batch. And so the batch quantity can be higher than the number of tokens to release. It can be lower than the number of tokens to release. It can be the same value. It really just kind of depends on how you want the batch to be aggregated. So in that way, like I said, it behaves like a combiner in join mode, because you can bring many tokens together into one token, or many tokens together into a few tokens, or it behaves like a separator in split mode, where you can receive a few tokens and release many more tokens, or it can behave like the combiner in batch mode, where you receive a number of tokens and release the same number of tokens if you want. It's just about how you want the individual members of the batch to be treated once the batch is complete. Now, the batch activity ends up having a lot of uses in a lot of different ways, but because it's so abstract, sometimes it can be kind of difficult to wrap your mind around. And so the way that I'm going to introduce the batch to you at this point is to use the batch as a way to know how many times something has happened. It's a really common thing in a lot of models I've seen where there's some behavior, some bit of logic that needs to happen only after something else has happened like X number of times. And the batch potentially is a good way to manage that because of its way of allowing you to collect a number of tokens that represent something and then releasing a token once the batch is complete and allowing further logic to be executed. So to kind of give us an idea of this, I'm going to go back to my little example model. And let's say that after 5 flow items have been processed by the processor, we want to just change the processor's color. Now, again, changing the color of something, I'm just using it as a representative way of saying you could do anything at this point, but we're just going to say that every 5 flow items is going to cause the processor to change color. Because there's plenty of times in a model where you might say after 5 occurrences of this, something happens. And rather than defining like some big complex logic, we're just going to say it changes the color, but that can stand in for any behavior potentially that you could want. So let's take a look first at the batch. I'm going to bring in the batch and put it right after the release activity. I'm just going to drop it right there so it splits my connector. And in the batch, we have a property that allows us to say how many tokens are going to be collected. So if we were to put in a 5 here, that means that 5 tokens will be collected by this batch. And then if we put in a 1, that means that 1 token will be released by the batch. And so similar to what we saw with the combiner in join mode, that means that the other tokens that were part of the batch are lost. And they all now are represented by this singular token. Any individual identity that was being carried by the tokens that were members of the batch is lost in favor of this new merged token. Kind of like, again, with the combiner where you take multiple flow items and merge them kind of into one. Same idea here, but now with tokens. So if we leave it on this 5 to 1, let's just see what that looks like before we do anything else. So if we hit reset and run, now, again, the rest of the model is going to behave the way that it always did. But now when a token gets to the batch, we're going to see a progress bar that shows that we are 1 out of 5. We are 1 out of 5 of our batch size. And so when the next flow item arrives, or excuse me, yeah, the next flow item arrives, we get a token that now says that we are 2 out of 5 when we finish the process. And then 3 out of 5, and then 4 out of 5. And then when we get 5 out of 5, that token gets released out of the batch and it goes to the sink. So if you look at the sync statistics, it has received 1 token that was made up of 5 tokens, but the sync just interprets it as 1 because it looks like 1 token when it comes in, so it's treated as 1 token. Right, so the batch takes this many tokens and turns it into this many tokens. And so if I were to put in a change visual activity right after that, whoops, I can say that we are going to set object color, and the object whose color is going to be set is the processor, and we'll just let it be random. And so now every time we process a flow item, it gets added to the batch, or rather the token that's associated with gets added to the batch. And then when the batch is done, it changes the color of the processor. And again, this idea of having the change visual in there stands in for whatever other logic you might want to do. But it's just being, again, kind of like the batch is a gatekeeper that says we got to collect 5 of those tokens that represent 5 process flow items before we can continue on to the next step. So it doesn't happen for every flow item. It only happens after 5 flow items have been processed because of the batch activity. Any questions?
Just a question. I don't know whether this comes later, but let's say you have two processors and you want to give a task to travel to any one of them. Can you select multiple processors as part of the same task? Travel to processor one. Can we combine two processors, select them together, or get them together?
Yeah, sure. Like in this case, like you mean like here, I'm always
processors in
taking
parallel,
something to
yeah.
processor one.
Yeah, let's say two processors in parallel, processor one and processor two, and the operator can go in either or, either
Right.
part of,
Yeah. You could do that pretty easily by just changing the model a little bit. Like if we had a second processor out here, with making the least number of changes to the model as it is, I could say, okay, here is a group of processors. So I'll say this is a group, and we'll call these my process group. And I can change the resource so that rather than just being an abstract reference, I could say, well, actually, this resource directly represents the group. And then when I do this, when I acquire the processor that I acquire becomes the resource, which allows me to do some pretty cool things where I can say, okay, I'm going to, yeah, we'll keep that the same so far. But now when I say unload, instead of unloading to processor one, I can say unload to whatever resource I acquired. Because now the resource isn't just a numeric value, it's actually a reference to the processor that I acquired. So I can only do this after the acquire.
Okay. But you won't be able to use the travel then, because the travel directly goes to processor one.
Yeah. This part would be a little bit wonky. So I might like create instead like a location that's kind of like a waypoint. Let's see, like if I were to go over here and just create like a little, this is an object that doesn't have any functionality except it gives me a location in the model. So I kind of make it kind of small and out of the way. And so rather than saying travel to processor one, I would travel here. And then when I unload to the resource that I acquire. And when I wait for event, I don't wait for processor one to do something. I wait for the resource that I acquired to do something.
Okay.
And then,
sorry, go ahead. Traveler to processor, I mean, is there a way we can change the task of travel to the earliest finishing processor or something like that?
You mean this one?
Yeah, I mean, if we select the processor group and we say processor one is going to finish first, so let's go wait there. Processor two is going to finish first for the operator to make a decision on the fly. Instead of
you probably could, but with what we know how to do, it would be pretty complicated. And it's easier just to use a stand-in object like this to say, kind of go towards the object, but of course it only works if they're reasonably close to each other, right? But because the acquire ends up kind of being the gatekeeper there, then you would have to have some way of being able to anticipate, well, who's going to finish their process first. And so you would need to kind of know like how much time is remaining on their process, which is kind of hard to know, but you could do it. With labels, you could like figure out like how, like when they arrived and know what their process time is going to be, and know that if it's before like this amount of time, like whatever is greater, the end time for processor one or the end time for processor two, that's the one that you're going to walk to, you know what I mean?
Yeah, no,
so you could definitely do it. You would just have to do a little bit more work on your own.
Got it. No, I was just in the angle of asking if there's an option inside the travel task itself which does that.
Yeah, for sure. Right. And so if we just finish the thought, when it comes time to do the change visual, now I can say that instead of always changing processor one, I made a label called acquired on the release activity where I can say, remember what resource you had acquired after you release it. So that when I get to the change visual, I can say, hey, whatever you acquired before, that's the thing that you're gonna mess with. And so now So we go to processor 1, and then we go to processor 2, and it has a, so again, it's going to happen every 5, right? So it's whatever we acquired last, but every 5 flow items, regardless of when they're going to be processed. So I can make this a little bit better and say that it, each processor gets its own batch by saying that we want to group the batches, by what was acquired. So there's this little group by option where I can where rather than collecting one big batch of 5, I can collect 2 separate batches of 5, one for each processor. Right, so now we've got 1 batch for processor 1, we're 1 out of 5 for processor 1, and now we're 1 out of 5 for processor 2. So now we have to wait for both of them to finish their batch before they change colors. But yeah, all cool stuff that we can do. There's a couple of new things there that you don't really need to worry about for future examples, but they're good ideas to have out there, like this ability of using a resource to represent a group of actual objects rather than just an abstract idea of availability. That can be really useful because it allows you to do stuff like this, right? Where you can say that, if I acquire something from that processor, then I can reference it again as like an unload destination. I can reference it again as something that I can listen to on a wait for event. And if I preserve that value after I release it, then I can also do other stuff with it out here, like with my batch and my change visual. So there's some neat things there. You don't need them for the exercise that we're going to do. You really just need the basic capability of the batch, but they're good things to know that they're possible. Cool. Any other questions so far? All right, now I can give you guys an exercise to do. So in this model, we're going to build a little simple model with these objects. So we've got a source that feeds a queue. We've got an operator, a processor, and a sink, and then another queue out here. And we'll talk about what that queue is for in a minute. So the processor and the queue need to be able to request the operator to do some task sequences. So that's why we've got the center connection there. And in our item description, or in our model description, we're going to say that an operator is responsible for transporting flow items from a queue to a box labeler machine. That's what we're using the processor for. It's just a standard processor, but we're saying it's being treated as a labeler. The idea being that every time we process a flow item, we are consuming a material, and that material is the label that actually gets put onto the box. And so the operator is going to be responsible for carrying things from the queue to the labeler, and then also being involved in the setup time of the labeler, which takes 2 seconds. And that section of the model is all going to use standard object logic. So you can use the use transport task sequence to bring things to the labeler. You can use the use operator for process checkbox to use, or use operator for setup checkbox to use the operator for the setup time. But then we're going to have this extra thing that says that every time we process a flow item, we consume a label. And once we've processed 15 flow items, the machine runs out of labels. And so we need to replenish our supply of labels at the processor, and our operator is going to be responsible for executing a task sequence that represents the replenishment of that material at the labeler. So that means that after you need to know how many flow items the processor has processed. And so every time you process 15, you want to start a task sequence that will tell the operator to travel over to this queue and load a created flow item that represents the replenishment stock, and then bring it back to the operator, or bring it back to the processor, and execute a delay time equal to this triangular distribution to simulate the reload time for putting the new supply of labels onto the processor. Now, one thing I'm going to tell you, do not unload the flow item that represents the replenishment to the processor. It may cause your processor to get very angry and blow up. So instead, what I want you to do is use the delay time to simulate the time it would take to reload the machine, and then just destroy the flow item when that time is over. Don't give it to the processor. You just want to destroy it. And you can either destroy it with a destroy object activity, or you could unload it to a sink if you wanted to. Either one of those options is fine. Just don't unload it to the processor. Okay, so your task sequence is going to say, I need to know after 15 flow items have been through the labeler, create a flow item over here in the pickup area, tell my operator to travel to the pickup area, load the replenishment, travel back to the labeler, delay for the triangular distribution of time, and then destroy the flow item, and then finish the task sequence. And so this is an example of doing something with a custom task sequence that the objects just don't know how to do, right? There is no replenishment option on any of the objects in FlexSim. So this is a way for you to say, I know that I need to execute this replenishment event every 15 flow items. So how am I going to do it? I'm going to do it with a blend of object behavior and process flow behavior to create my own custom task sequence to cause this replenishment event to actually happen. Okay, any questions there? Okay, take a few minutes to work on that. This will probably be in the 20-minute range or so. If you have questions along the way, feel free to let me know. And then we'll do a walkthrough when you've all had a chance to give it a try. So good luck. Okay, so this model isn't very complex in terms of like what it looks like, right? It's just a couple of objects that we've been working with before. But the customized task sequence part of this can be a little bit tricky because there's a little bit that we have to think about managing. So I'm just going to first set up the first bullet point part of the description where we're going to have the operator transport flow items and also process them at the processor, or rather be involved in the setup time at the processor. So if we just go like this is all just the standard stuff that we've been exposed to already. And the inter-arrival rate on the source, the default here is fine. We'll say use transport so that we use our operator. And then on the processor, we've got our 3-second setup time, and we're going to use the operator for setup. And that's really all we need to do for the first bullet point, right? And so now boxes arrive, operator walks over, picks them up, drops them off. Cool, right? So far, so good. So the second bullet point is where things get tricky, where every time this processor finishes 15 flow items, we need to trigger like a replenishment process. We want to say that there is some other flow item that represents like a replenishment stock of things where we need to bring it back to the machine. So the first thing I'm going to do is create an object that represents the place where we store the replenishment. And this can really be, you know, anything. It doesn't really matter where you put it. I'm just using a cube because that's pretty simple and straightforward. And then in my process flow, the first thing that I need to think about is how am I going to know when a processor finishes processing 15 things? Well, I can know whenever a processor finishes processing something by using an event triggered source, right? If I use an event triggered source and say, listen to the on exit event. And there are a few events that you could listen to here. You could do on exit. You could do on process finish. Doesn't really matter. We're just looking for an event that says we have, you know, in like concrete terms, we've put a label on the box, which means we have one less label than we had before, right? And so if we do this where it says finished processing, then if I just run it the way it is, right, we're going to get a token every time something finishes. So there's one token, 2, 3, right? Because we're getting a token for every single one of these these events. So this event has now happened, however many tokens that is. You know, if we make it smaller, oh, perfect, I got right on 15, nice. So that's kind of what we're looking for, right? We want to know when we've created 15 tokens here, because that means that we've had this process happen 15 times. So I need a way to turn these 15 tokens into 1 token, because I need to know if I've collected 15, and if I have, I can move on and do the next part of the model. So this is where the batch comes into play.
So I forgot the difference between on exit and send to port. Could we use either for this one?
Yeah, that would have been fine as well. It's just in terms of, it just changes things in terms of the timing a little bit. So like if you remember this slide where we're talking about order of execution, right? Send to port fires at this point of the execution, and on exit fires way down here at this point. So there's just a few events in between those 2 events, but they happen really, really close to each other in terms of time.
Okay, thanks.
Yeah. Okay, so now I have my batch, and we're going to say that this is going to be a 15 to 1 batch. And I'll call this batch collect 15. And so if we ran this again, right, what we would see is, you know, we'd see slowly over the course of time, we were building up tokens up to our batch. And once the batch finishes the batch, if it doesn't have anywhere to send it, they just sort of like disappear. But we're going to give it somewhere to go, so this doesn't look too strange. So now we have to decide, well, what do we want to do if this event happens 15 times? Well, the first thing that you might do is say, well, let's create an object. And we'll say create replenishment flow item. Meaning that we're going to create a flow item that represents the replenishment that we need to bring to the processor. Now, it doesn't really matter what kind of object that you create, but just for fun, I'm going to say that we create a cylinder, and I'm going to create it into Q2, and we will refer to it as just item. So again, if we just kind of see where we're at so far, reset run. Now, whenever we collect 15 of those events, we get a token that creates a cylinder into the queue. So that means that once we've created that cylinder, we want our operator to go and get it, bring it back to the processor, simulate the time that it takes to restock the machine, and then remove the cylinder because ostensibly it's been reloaded into the machine. We don't need to represent it visually anymore. So that means that I need a task sequence. So I'm going to start by saying create a task sequence. And I'll call it replenish machine. We are going to give this task sequence to the operator. And then we're going to give them the first step. And the first step is to say that we are going to travel to the pickup point. So this travel is part of our task sequence, and our destination is Q2. And then we want to load the item that we just barely created. So again, as part of our task sequence, we're going to load the item. And then we need to travel again. And this time we're traveling back to processor 1. And so you might call this like travel to empty machine. Maybe call this load stock. And then we need to simulate the time that it takes to replenish the machine. So I'm going to use a delay activity that comes out of the task sequence section of the library. Now, most people don't realize that that's there, and that's fine. And they end up using the regular delay to do this, which would have been okay. the reason though that I would recommend using this delay versus this delay is because even though they both have the ability to delay, right? The difference between them is that the task sequence delay has this additional state option. And the state here allows us to put the operator into a state for the duration of the delay time, whereas the regular delay doesn't have that ability. It just is a delay that the token experiences, whereas this delay is treated as a delay that the operator experiences by putting him into a different state. So you could say that like maybe during this time, the operator is considered doing like maintenance or changeover or some other, or like filling maybe, or some other state that better represents what the operator is doing as opposed to just being like idle. So in this case, I'm just going to say maintenance. And my delay time is going to be triangular. And it's just going to be the default options, 5, 15, and 10. And so once that delay is over, we can finish our task sequence. We don't have to do anything else. And then we will do a sync activity to represent that the replenishment event is over. And so if we run it, whoops, cancel. So we're collecting all of our tokens. So here we're about to get our 15th, and that causes the operator to go fetch the cylinder, bring it back, do the delay, and then the cylinder, I forgot to destroy it. So now he's carrying the cylinder and the box. So this is why I said that we need to destroy the cylinder, either by unloading it to a sink or by just destroying it using destroy object, because we don't want him to carry that cylinder around forever. So we're just going to say that you're going to destroy it there. So now, again, I'll just fast forward through this so that we get all 15. And again, operator is triggered to go and fetch the cylinder, bring it back, do the delay, and then goes and gets the next box and just keeps working as normal.
Is there a way to make the processor idle as well during the, I guess, reloading?
Yeah, so let's see what state it goes into naturally, because it might be like waiting for operator or something like that, depending on what goes on. So with mine, well, in mine, it naturally goes idle. So I don't have to worry about managing that. But depending on what event you listen to, like you could have like brought the flow item to the processor and then triggered the replenishment. Like if you listen to on entry instead of on exit, like I did, then you might have to put the operator into a different state, because then you would be waiting for operator. And yeah, using other activities like there's an activity we haven't talked about yet, but hopefully we'll talk about it tomorrow, called custom code, that has some options for telling an object to go into a particular state. And so you could like drag that activity somewhere and say, hey, you should not be like waiting for operator right now. You should be like in replenishment or something like that.
Okay, cool.
So otherwise mine just shows up as idle. And if I wanted it to be in a different state than that, then I could definitely do that again with that like custom code thing. In fact, let me just do that because that's actually kind of fun. So if we grab custom code and say, you know, I'll just put it right here and I'll say that we are going to control the object by doing a set object state. And we're going to set the object processor 1 to the state of, we don't have a replenishment one per se, but you could make one, but that's a little bit more into things that I want to get. So we just call it like maintenance. So now when we run this, we'll see that the processor goes through its normal states of processing and idle and processing and idle and all that fun stuff. And then when the replenishment happens, rather than being idle, we'll see it go into this maintenance event, which will show up properly on the reports that we generate. And then when things pick up again, he'll just go back, the processor will go back to its regular setup idle processing sequence. If you wanted to be like really particular, you could have done another custom code activity after the task sequence was done to set the state back to idle, because you don't maybe want to let the operators travel to the queue also count as maintenance. Maybe that does actually count as idle, but you know, you're getting into like really detailed there about trying to manage like what's the, you know, the uptime of the machine, you know. But those are good questions, good things to think about. And so to kind of answer the question on the description about what the operator's utilization rate is, this is a good opportunity again to use a dashboard, where we might say, let's have a blank dashboard, and we'll use the state chart, use the pie chart, why not? And we'll say that I want to get the states of the operator. And when we hit reset and run again, now one thing that's kind of interesting here is notice that we have this value in the middle of the pie chart that tells us the utilization rate. So it says that he's 46.5% utilized, and what all accounts for utilized. So if we stop the model, we can see that traveling while empty accounts for 14% of our utilized time. 16.7% counts or is our traveling while loaded. Offset traveling while, or actually, wait, which one is that? Yeah, it's the offset travel empty is 0.94% of our utilization. And then being utilized is part of our 14.82%, which is all counted for the setup time. That utilized time is counted as the time being involved with setup. But notice that maintenance here is 3% of our time. But because it's kind of like this, this shaded out color that's kind of like the idle, that's actually not being counted towards our utilized time. That's actually being counted towards this non-utilized time. So if I go to the chart, if I want to say, well, actually maintenance should be included in my utilized, there is this section of states underneath the chart options that lets me choose what state should be counted as what kind of utilization calculation. Should it be not utilized, which is this blank field, or should it be utilized, which is this green field? And so if I click on maintenance, now it says that it's utilized, and now that gets counted towards my utilized time. And so now if I hit reset and run, it'll account maintenance towards my total utilization rate, which gets us closer to 50% utilization. Now in that chart, you have the ability to choose how different states that an object is going to go into affect its utilization time. So like I said, a blank cell means that it's considered not utilized. If it says the word utilized in green, that means that it is utilized. And we don't have one in here, but if you click again, there's also the option to say that it's excluded, which means that this state would be excluded from either being utilized or not utilized. It doesn't become part of the utilization calculation. So it's not a yes or a no. It's you know, here's something that's utilized, here's time spent being utilized, here's time spent not being utilized, and here's just time spent that doesn't count towards either one. So you can kind of pick and choose how you want that to be accounted for. Hey, any questions there at all? Okay. So hopefully you guys didn't have too much trouble with this example. I really like this this model in particular in the training, because I think it's something that comes up really, really frequently. And it's a really good example again of where you might blend process flow pieces of a model with object-based pieces of a model. In this case, really doing something that the objects don't know how to do out of the box. And so we're really supplementing their behavior with this process flow. And like I said, this is the sort of thing that you do in projects, right? Where you need a way to cause something to happen. The objects don't know how to do it. And so by using a few activities, we can gain control over our operator enough to tell it to do what we want it to do. Okay, so let's take our afternoon 15-minute break. Let some of this sink in. And when we come back, we're going to shift gears a bit and talk a little bit about how to use conveyor objects in our models. We really just sort of barely scratched the surface with conveyors before. So we're going to do a deep dive on conveyors in the next section. All right, I'll see you all back in 15 minutes. All right, so like I said before the break, this next chapter, we are going to be jumping into learning about the conveyor objects. The conveyor objects are actually a very, very deep tool. You could probably spend at least an entire half day, if not more, of training just talking about all the different capabilities and functions available in the conveyor objects. And I'm going to try and give you guys the highlights in about an hour or two. So the conveyor objects are a little bit different from the regular objects, but they do have some similarities. The similarities are basically like the way that they tend to receive flow items and send flow items. You make port connections to them and from them, and you're allowed to have flow items come to conveyor systems and travel around in the conveyor, like kind of like what you're seeing here on the screenshot. But they also have a lot more capabilities beyond that, like being able to really mimic a lot of real world conveyor behaviors, like doing slug building and merge control, setting up photo eyes for complex logical problems that you need to solve while flow items move around in the conveyor, and just a lot of things based on where flow items travel within the conveyor system. Because the conveyors are, excuse me, because the conveyors are so, I guess, like entrenched with the 3D environment, a lot of the things that we do in the conveyor system are based on where flow items are located, right? And it kind of makes sense, right? Because in real life, conveyors have they have speeds, they have distances, they have twists and turns and inclines and declines, and we try to be able to mimic all of that within the conveyor system. And a lot of the logic that happens while flow items are in the conveyor system then are therefore based on where they go and what they do when they get there. And so we provide a lot of different functionality to control these kinds of ideas. And all of the objects that are related to the conveyor behaviors are located in a special section of the library devoted just to the conveyor objects. And this is actually an older screenshot, unfortunately. But if you go over to FlexSim and take a look at the object library, you'll notice that there is a section dedicated to conveyor actions, conveyor behaviors. So all of these objects are related to building up and controlling the conveyor objects. Now, in the slides, there are a lot of slides that I'm not going to directly talk about, but they're a good reference for describing the different parts of the conveyor library, like how a straight conveyor versus curved conveyor work, and then some also important things like decision points, stations, photo eyes, and some of the other objects that we're going to talk about in the conveyor library. So I'm not going to talk about each one of them, just as in terms of a lecture, because I think it makes more sense to see the stuff in action than it is just to kind of talk about it. So if you want to refer back to these slides, that's great. They're provided as a way to provide useful definitions about what these things mean. But the main thing is to see how they work together. So I'm going to go back over to a model, and we're just going to make a new model here. And let's talk first about creating conveyor objects themselves. So I'm going to use the baseline units here. That's fine for what we're doing. And then in my library, I'm going to start by creating a conveyor object so that we can just kind of get to know it a little bit. Now, if you do a single click on the conveyor object in the library, it gives you a choice of either making a straight conveyor or a curved conveyor. And so if you choose one of these, it puts your cursor into a conveyor creation mode. Now, this conveyor creation mode allows you to create a conveyor of a customized size and orientation. And so in this mode, you click once in the grid. So that's just a single left click. And as I begin to drag my mouse, it begins to drag and create a section of conveyor. So if I stretch my mouse further in any of the directions, then my conveyor gets longer. If I move my mouse around, it allows me to change the orientation and the direction that the conveyor faces. Once you've kind of got the conveyor positioned the way that you want, if you left click again, that finalizes the conveyor segment. Now, when you finalize the conveyor segment, you'll notice that the conveyor is now highlighted in yellow. And there are some things to point out that you can see on the conveyor. So if we zoom in just a little bit, first thing that you'll notice that you may notice is there are a couple of arrows that point in the direction of flow item flow. Okay, so that would mean that if flow items came onto this conveyor, they would flow from left to right, following the direction of the arrows. Now, at the ends of the conveyor, there are also a pair of red crosses that allow us to change the size and orientation of the conveyor. So if you click on one of the red crosses and drag, then it allows you to, again, be able to manipulate the dimensions of the conveyor. Now, also, when you click on the conveyor, you'll notice that the properties show up on the right-hand side, just like any other object, where we can establish things about like whether or not the conveyor is accumulating or not, what the speed is in terms of our model units, acceleration rate, deceleration rate, and then some rules about spacing on the conveyor, like stopping space, moving space, if there's a delay for restarting. There's also a fixed interval movement option to allow the conveyor to behave like a power and free, where there are like dogs that move along the conveyor and you can only attach flow items to the dogs rather than being able to be placed anywhere along the conveyor. And also whether or not this conveyor is going to perform slug building for like a sawtooth merge type of operation. Now, in the conveyor behavior options, there's a lot of information here, of course, about how these things work. And so to kind of help out, we've created tooltips so that if you mouse over them, they're going to try and give you a hint as to what these things mean and how like these spacing rules and whatnot are going to be handled. These are also very well documented in the manual. If you want some more information about things from the manual, you can click on the question mark here to get to the manual page for these sets of options. Now, one of the ways in which the conveyor object is different from some of the other objects is how we handle things like coordinates and the location of the object in space. So just to compare, if I drag out a source object, this is something I don't think that I mentioned specifically, but when you click on an object, one of the sets of properties that you see is its location in the Cartesian coordinate system, where you have an X, Y, and Z location. And this X, Y, and Z location by default is based on where the blue cone of the object is placed. So that means that the blue cone is located at the negative 9.47 meter in the X axis, 0.47 meters in the Y, and 0 axis in the Z, or 0 meters in the Z. Now, the conveyors, if you click on them, they don't have those cones that let us know where it's positioned. And because the conveyor is long, it doesn't really make a lot of sense to describe the location of the conveyor as a single set of coordinates. So what we did instead is we have start and end points on the X, Y, Z axes. So you can see where the X axis of the conveyor begins and ends, where the Y axis begins and ends, and where the Z axis begins and ends. And this allows us to do some neat things with the conveyor. Like, for example, I mentioned that the arrows point in the direction of flow. If you're looking at your conveyor and the direction is actually facing the wrong way for you, you want them to actually flow, in this case, maybe from right to left instead of from left to right. If you come over to the start and the end point for the X, Y, and Z axes, there's this little button that is called the reverse direction button. And if you click on that, it just reverses the flow on the conveyor. Now, this isn't something that you would do during model runtime, change the direction of flow in the conveyors. We have other tools for things like that. But this just allows you to say, oh, I oriented the conveyor the wrong way. Let me just quickly flip the direction around so that the conveyors are going to flow in the direction I want. And what it does, you'll notice that it just changes the, in this case, the X and the Y direction so that the flow goes in the reverse. Now, if your conveyor is oriented maybe this way, more along like the Y-axis, then the reverse direction just reverses the Y-axis. It's smart enough to know which way it should reverse in order to allow the flow to reverse in the right direction. Now, another reason why these start and end points are kind of useful is because of the ability to change the Z-axis if you wanted to. Like, for example, if I said that the end Z was 3 meters, then that allows me to treat my conveyor as like a ramp. And if I said that my endpoint was 0 in the Z, then allows it to go down like a ramp. So the conveyor objects are definitely designed to inhabit the 3-dimensional space. So if you need them to go up and down to different levels and different Z axes, that's perfectly fine. And it's just a matter of changing the start and the end points for any of these axis points, and you can manipulate them. Now, in addition to all of that, there are also a set of visual options that you can change about the conveyor. By default, the conveyor is meant to look like a simple roller conveyor. Whoops, you can do that. And on this drop-down menu, you can choose other pre-built visualizations. And you can also use our interface to create new visualizations. Like, for example, if you switch it over to the belt conveyor, it looks like it's a belt. It gets given like a black belt that's drawn over the top of the rollers. But if I wanted to change it even more than that, I could go to, say, new visualization, and it will give me a window where I can change different aspects of the conveyor, like whether or not I want to draw rollers or not. So if I check or uncheck that, right, and say apply, then it will draw in the rollers. If I want to show the belt, I can choose different textures that I want to use to represent the belt, maybe something like that. You can even show whether you can either decide whether or not you want to change the size of like the side skirt, if you want to add a texture to the side skirt, right? Just kind of change things up a little bit if you want to add some nice visual niceness to this. And there's also different rules for how you might want to handle the legs, where the repeat distance is how often a leg is drawn on the conveyor. So right now with a repeat distance of 10, you'll get a set of legs every 10 meters. But you can also change that unit to a different unit if you want to be like maybe every 6 feet. Right, so it looks like something like that. I think this already has so it has a leg height rule so that it automatically sets the leg height from the lowest point of the conveyor, so that it just always looks like, it's got support structure beneath it. I don't know if you noticed it, but when I dragged out the conveyor initially, it didn't have that. Right, if I change the end point here, the default visualization doesn't automatically make the legs the same height as its lowest point, but this option automatically draws in the supports correctly, which is kind of nice. And that's a nice thing to be able to change depending on how much detail you want to put into the conveyor objects. And once you create a conveyor too, you can always flip its visualization. So I can say, well, actually, I want to use this new visualization I just created with the leg frequency and the belt type and the rollers and the side of the legs and the side skirt texture and all that kind of fun stuff. Any questions so far? Okay. So let's say that we will actually want to get some flow items onto this conveyor. This is a way that the conveyor objects are actually very similar to the other objects. If I wanted the source to be able to send flow items to the conveyor, all I have to do is make a port connection from the source to the conveyor. Now, before I click on it, though, I want you to pay attention to what the conveyor looks like right now. And notice that when you create the port connection, there's something new at the end of the conveyor. Okay, that wasn't there before. And if I delete it, my port connection goes away. And if I make my connection again, I get this little white square at the end of the conveyor. And this is actually a separate object. This is an object called an entry transfer. An entry transfer is a special object that's created automatically when creating port connections on a conveyor that allows for flow items to transition from outside the conveyor system to inside the conveyor system. So in order to allow a flow item to get onto a conveyor, it must pass through a transfer. That's why when we make the port connection, we automatically create the transfer and position it on the conveyor. Similarly, if we want to get flow items out of the conveyor, if I make a connection from the conveyor object to the sink, it draws another transfer. It's another white square that I can click on and kind of move around. This is called an exit transfer. And this is a way to get flow items out of the conveyor system and into some other external object. Okay, now there's a couple of interesting things about the conveyors, or rather about the transfers. So I'm just going to zoom in for a second. And if we run, I want you to notice where the flow item is placed when the flow item first arrives. So rather than letting it run, I'm just going to stop and I'm going to hit step for the first arrival. And here's our first flow item. And you might notice that it's located right above the transfer. In fact, I can still click on the transfer from underneath the object. Because wherever the entry transfer is located, that is where the flow item will begin its flow on the conveyor. That means that if I want to change where the flow item originates on the conveyor, all I have to do is move the transfer. I can click on the transfer and drag it off to the side. And then when I step forward and get my first flow item, the flow item is placed right at the middle of the transfer. And then when you run from there, it just continues its flow down until it reaches the exit transfer, and then it goes out to the sink. Okay, now you can have as many entry transfers or exit transfers as you want on a conveyor. You can have multiple drop-off points onto a conveyor object or into a conveyor system. Have as many pickup points off a conveyor system as you want. If I just were to create another object, just like another source, and make a connection, it's automatically going to give me another transfer that I can decide where I want flow items from this source to be located when they originate on the conveyor. So it really is pretty flexible. You don't have to have everything come in and come onto the conveyor system at one common point. You can basically put things onto the conveyor anywhere you want. And if you have like an operator dropping things onto the conveyor system, they automatically know how to place things onto the conveyor objects as well. Like if I were to say that this source uses transport, that's going to create a task sequence for me that will allow my operator to drop flow items off at wherever the transfer point is on the conveyor. Now we can do the same things with the exit transfer. Notice that the flow items will naturally flow down to the end of the conveyor because that's where the transfer is located. So they reach the end of the conveyor, find the transfer, and then they're just sent out to the sink. And so if I reset my model and move the transfer around, I can also change where that exit point is for the conveyor. Right. So they only flow as far as the transfer now, and then they get taken out of the object. Now we can also use task executors to take things off the conveyor system. So like if I have another operator here, Now, this is one of the ways in which using the conveyor objects can be a little bit tricky. If we look at the properties for the conveyor object, notice that on the property set for the conveyor, there is no mention of things like send to port or use transport. That's because the conveyor is not in charge of sending flow items away. The exit transfer is in charge of that. And so if you click on the exit transfer, we get a different set of properties, which allows us to do things that we're familiar with, like sending to a port or requesting a transport. So if I want the operator to transport things to the sink, I need to tell the transfer object that it's using transport. And I need to make sure that when I make my center port connection to communicate with the operator, that the center port connection goes to the transfer and not the conveyor. Now, because the transfer is so small, it's really easy to miss. So you got to make sure that when you put the connection cursor on it, that you look for the yellow highlight that pops up to let you know that you're on the transfer. If I get on the conveyor is going to highlight in yellow, and my transport won't work because it's not connected to the transfer. So I'm going to make sure that I'm connected to the transfer. And now when I run my model, flow items will come down to the transfer, stop, and wait for the operator to pick up the flow item and carry it to the sink, just like it would for any other object. Okay, now that's nice, but the transfers actually allow for some other pretty cool behaviors, especially when related to the task executors, where if you click on a transfer, you have the ability to stretch the transfer to be a larger area. And so if you make the transfer a larger area, then we allow for the operator to anticipate and potentially intercept where the flow items need to be taken off the conveyor. So if they make it all the way to the end, then they make it all the way to the end and they stop. But if the operator sees it coming, you could actually pick it up anywhere from within this area defined by the transfer. So the flow item doesn't actually have to stop unless it reaches the end of the transfer area, which is the very front part of that transfer object, and allows the operator to grab flow items anywhere from within within that little zone, I guess you could call it. So that's kind of a neat feature. That's something that none of the other objects know how to do, but the transfers do that because it's such a typical thing to have pickers grabbing things off a conveyor anywhere within like a range of possible pickup points. And so that's what this is allowing us to do, is to define a range where the task sequence is created and the operator has the potential to pick up the operator or pick up the flow item anywhere from within that that transfer area. Hey, any questions there so far? Okay, so the entry transfer and the exit transfer then are a mechanism that allow flow items to either enter or exit from the conveyor system. There is a third type of transfer that allows for flow items to transition from one conveyor segment to another. So if I create another conveyor, I'll keep it consistent. I'll just change the same visuals that I have. Now, if you have two conveyor segments like this, and you drag one into the other, the conveyor does like a little magnetic snap onto the conveyor. And you can see that it actually draws a little square in between them. Now, the side skirts look kind of weird when you're doing this sometimes, depending on the visualization that you chose, but it's just visual, it's fine. And this little square that I can click on, this is a type of transfer that allows for transitions from one conveyor to a side conveyor. So we call this a side transfer. And so if I remove the exit transfer just for a second, then that means that my flow items are going to take that transfer and just transition off to the side as though pushed down the side conveyor. Okay, so how do the flow items know to take that transfer? Well, so this is actually an interesting problem. So let's put that exit transfer back for a second. And so if we run the model the way it is right now, flow items are drawn to the exit transfer. Okay, so we're going to start getting into a little bit of information about how flow items find their paths on the conveyor object. And so the default pathfinding method that we're using here says to stay on your current segment as long as you can and take the last transfer that you see on this conveyor segment. So that means that if I move the exit transfer to over here, then my flow items will instead be drawn to the side transfer because that is now geographically the last transfer on the object. So again, the default pathfinding mechanism so far that we're seeing says, stay on your segment until you find the last transfer and then transition to wherever that transfer may take you, whether it's an exit transfer that takes you to an object or a side transfer like this that takes you to a side conveyor. And now we've got some blocking because our flow item here is in the way, blocking the progress of this flow item. And that's something that can happen. So that's fine. Okay. Now, another kind of transfer that's going to be important to know about is what's known as the inline transfer. So I'm just going to move this conveyor kind of up and out of the way for a second. And I'm going to demonstrate the use of an inline transfer while also demonstrating a tool in the library called the join conveyors tool. So the join conveyors tool is a handy way to easily create curved conveyors between perpendicular or nearly perpendicular conveyor objects. So if you choose the join conveyor tool, you can see that it changes the cursor into this join mode. And then if you click on the sending conveyor and then click on the receiving conveyor, it'll automatically fill in the curve that you would need to join those two segments together. And again, because it creates transfers. So here we have an inline transfer that transfers from the inline flow of this conveyor to the inline flow of this curved conveyor, and also another inline transfer from this curved conveyor to the straight conveyor. Same rules apply that if my exit transfer is further upstream, then the inline transfer is going to be preferred by the flow items. But notice how it allows for a nice and smooth transition onto the next conveyor as they just follow that curved segment. They get off the straight segment at the transfer point, and then they get onto the curved section at that point, and then continue on to the straight section after that. Okay, so a lot of times when we're working to conveyor objects, then one of the problems that we need to solve is, what if I have some flow items that I want to send to this point on this curved conveyor and then to the straight conveyor, and I have some flow items that I want to send to the sink, to sink 1. So let's say I have some flow items that need to go to sink 2 and some that need to go to sink 1. Well, using other objects in the conveyor library, like the decision point, the station, and the photo eye, we can establish routing rules for how flow items travel through the conveyor system. Now, remember, the default pathfinding algorithm says we're going to stay on our current segment for as long as we can until we reach the last segment. But if we give flow items a destination to go to, then they will also try to find their own way to get there. They will naturally try to take the shortest path in order to reach some destination. So let's kind of take a look at that first of all. So to kind of help us with the routing, the routing of flow items in the conveyor system, I'm going to start with an object called a decision point. Now, the decision point object is dragged out from the library and placed onto a conveyor segment. If you try to place a decision point someplace in the model other than on a conveyor segment, then it doesn't do anything. You're not allowed to have a decision point just out here floating on its own. And one of the ways that you can tell that a decision point is not active is that it doesn't have the crosshair in between the diamond. So if I take this decision point and bring it back over to my conveyor and release my mouse, it draws in the crosshair to let you know that this decision point is properly attached to this conveyor. Now, the decision point object is a pretty, I guess, basic object. It doesn't have a ton of functionality built into it. The main ways that we utilize the decision point is through the application of its trigger events. And the two most important trigger events that the decision point has is the on arrival event and the on continue event. So the on arrival event happens when flow items arrive to the decision point, and on continue, like you might imagine, happens when flow items continue away from the decision point. So using the on arrival and the on continue triggers, we can use options that are built into those triggers to do different things, like to tell flow items maybe to stop, to send the item to some other destination, to maybe do some kind of a movement like a rotation or a translation. Other options that we're familiar with, like setting labels or setting colors. All these sorts of things can be done as one of the actions assigned to this trigger. Like, for example, if we do something kind of simple, we could say that we want to just give the flow items a random color when they arrive to this decision point. So if we hit reset and run, flow items come onto the conveyor system as a brown box, and then they just get given this random color as they travel down the conveyors. So they hit the decision point, and at that point, the on arrival trigger happens, and that sets their color. Now, one of the ways that the decision point is used most often is a way to control the routings of flow items. Now, if we look at the decision point, there is an option here, and we can go to the on arrival trigger and add an additional action that says that we're going to send an item. Now, sending an item using decision point logic is different than using like send to port logic, but we also tried to make it feel kind of similar. So the way that you use send item is you indicate a destination object as the destination. You want to say, this is where I want things to go. Now, notice this expression, you might recall this from Monday, that says that we are going to use the object that is connected to current on out object 1 as the destination. Now, right now, we don't have an out object because there are no port connections on this decision point. So if I were to make a connection to some other object, I could treat that as my destination. Now, there are some limits here of what we're actually allowed to do as a destination for send item. Like, for example, if I were to try to make a port connection from the decision point to this sink, it's actually not going to let me do that. Because since the decision point object is part of the conveyor system, it's not going to allow me to connect that out to another to another non-conveyor object. Decision points can only be connected to other objects that are part of the conveyor system. So that means that I can connect to other decision points. I'm allowed to do this and use that as my target destination. I can use stations as one of my targets. I can make connections between these two objects. That's fine. Or I could use photo eyes. I can make a connection between these two objects because they're both part of the conveyor system. That's okay. Or I could even connect to transfers. So I can make a connection from the decision point to that exit transfer all the way up there. Now, what's the difference between doing any of those three things or any of those four things? It really doesn't matter. In each case, we're just establishing the connection between the decision point and that other object as the target destination for a flow item. So it doesn't matter if I send it to the transfer or to the photo eye or the decision point, it's all going to behave pretty much the same. So if I use the transfer in this case and say reset and run, so now we have altered the default flow of the flow item because it no longer is using the default pathfinding method that says stay on your segment as long as you can. I'm now assigning the flow items an explicit destination. I'm saying that you flow here. And because the condition is true, this is going to happen for every flow item. Okay, so all I've done is I've said, okay, no one goes to sync 1, everyone goes to sync 2. What if I want to say that some things go to sync 1 and some things go to sync 2? Well, in that case, I can use multiple object connections as possible destinations for my send item. So just to demonstrate something different, I'm going to bring out a station object. A station object is basically a decision point that includes the ability to process a flow item like a processor. But it's part of the conveyor system instead of an external object that you would send flow items to and then bring back. It just allows us to say this is our processing point, potentially. So I'm going to make another connection from the decision point to the station. And on my decision point, I'm going to say that my send item logic is no longer to always send things to destination 1, my first out object. I'm going to say, let's choose a random output port. And that fills in a whole bunch of code that you don't have to worry about. But it's just going to choose a random port associated with the decision point. And so now, excuse me, now when we run, we don't know where they're going to go. They might go to sync 2, or they might go to the station and then out to sync 1. Right, and they go to the station and they stop because the station tells flow items to stop, be processed, and then continue when the process time is done. Okay, any questions at all? Okay, so that's using a fairly simple send item where we're just saying choose a random port. But you also notice that there's another option that allows you to do send item by case, which is a little bit more common. Really similar to the stuff we did with the decision activity and process flow, where we said that we have a case function, and then if the case function equals this value, then treat this as your destination, or if it's this value, treat it this is your destination, right? So you can set up, again, like a map that says that flow items with particular labels maybe get sent to particular destinations. Now, in all those cases, when we send the flow item somewhere, the flow items are going to naturally find their shortest distance. right? So if we tell flow items to go someplace within the conveyor system, you don't have to tell them to move every segment. So like notice here that in order to get to the sink, I don't have to say go to this segment and then this segment and then to the sink. The flow items are naturally finding their own way to get there if they're left to their own devices. The only thing that I have to tell them to do is to go to some destination, and they'll figure the rest out on their own. And it doesn't matter how many segment changes potentially there might be. If you were to have like, I don't know, something crazy like having a bunch of, you know, conveyors, like here's a conveyor that maybe locks on there, and then another conveyor that goes this way, and then another conveyor that goes off like that way. You know, just a whole bunch of different segment changes. If I want a flow item to end up like out here, I don't have to say, okay, transition to the curve and then the straight and then this and then this and then this. I can just put a target destination like a photo eye or something and say, go out here, right? And it will naturally find the shortest path that you need to take in order to get out there. You don't have to micromanage the flow unless you absolutely have to. Okay, now another really common thing that we need to be able to do on a conveyor system is controlling restricted areas, where there are parts of the conveyor where certain rules have to be enforced about like where flow items are allowed to flow. A lot of like traffic management, like managing what happens at like intersections where flow items might meet and how they merge with each other to make sure that, you know, they follow, you know, relevant rules about who's allowed to go where and when. And decision points, stations, and photo eyes become another good way to handle that. So just as like a simple little example of this, like if we were to have something like, let's say that I've got a source and a couple of straight conveyors, and I'll say that we've got one here. I've got another one over here. I'll put them kind of close to each other. And then I've got another conveyor that goes like this way. And I'll join these guys there and there. I'll say that we're just going to create a bunch of flow items that can go to either of these. So I'll say that we'll create flow items like every 5 seconds, and we can send them to a random port. So if we run this model the way it is right now, we're going to see that flow items are going to do kind of like a rudimentary merge control kind of on their own. Right, where they kind of like try and slide down to the curves. But when we start getting some competition here, there might be like near miss collisions, like right there, we got really close. There might be other times when the flow items do actually like kind of collide into each other a little bit. And so you may have rules that say like how close flow items are allowed to get as they merge onto this, like share, there was a collision right there, of like how close they can get to each other. And so this might be a reason to enforce a restricted area about how these flow items need to share this lane, right? And it really is kind of like a traffic problem, right? Because you've got like 2 roads that come this way, and you got another road here, and then we have like merge lanes where we want to be able to like get onto this this shared section of conveyor. So decision points, stations, and photo eyes, like I said, are a useful way potentially to enforce these kinds of rules. So if I want to create a restricted area around this set of conveyors, I can first drag out a decision point on the first conveyor, drag out a decision point on the second conveyor. And essentially what I'm saying here is that these decision points, or at least what I'm going to say, is that these decision points are going to function as entrance points to the restricted area. So you might think of them as like stop signs, right? Where if you're traveling along on the road, and you've got the stop sign, you have to like stop and like wait for someone to go by. And so this is going to be, these two objects will be entrances to the restricted area. And so on their trigger logic, I'm going to say on arrival to create an entrance to a restricted area. Now, when you set up a restricted area, we have this notion of an area owner. As you can see from the hint text, it says that we're defining, an object that owns the area and essentially becomes the manager of any acquisition requests that are being made on that restricted area. Because flow items are going to arrive to this decision point, and they're basically going to say, hey, can I use that restricted area or not? And the owner object is going to be the object that's in control of managing those requests. So both these decision points are going to do this. They're both going to say that we are entrances to the restricted area on arrival. And now I need to choose an owner object. And typically an owner object is another object like these. It could be another station or a decision point or a photo eye. Let's just use a photo eye just for fun, just because we haven't used one of those yet. And then on the photo eye, I'm going to use one of the triggers on the photo eye, and it has a different set of triggers because it has different events that you can take advantage of. And in this case, I'm going to choose the event that's called on uncover, because the on uncover event is the event that fires when the flow item clears off of the decision point. So when the trailing edge of the flow item clears the photo eye, that is the on uncover, event. Now for the on uncover event, I'm going to say that this is the exit from the restricted area. And so this object now will prioritize and manage any requests that are made on the restricted area. Now, in order for the restricted area to work, the entrances need to know who their owner is. And the owner right now is being defined as something connected to an output port. So again, I'm going to make port connections to define the area and say this is an entrance and this is the exit, and this is the entrance and this is the exit. And so now when flow items flow down here, if the area is clear, they're allowed to continue. But if not, they may have to stop and wait for the event that marks the exit from the restricted area, and then they're allowed to continue after that. So you can see here where the flow item might have to stop for a bit, and then when it's cleared, flow item is allowed to continue. And by default, the area is managed by going through the first come, first served on the requests. But notice that in the exit from the restricted area on the area owner, there is a checkbox that allows you to prioritize by some label value. So if there were some flow items that were considered more important that had priority on the merging lane, you could give them that priority with a label, and the area object or the area owner object would be able to manage that. Okay, any questions at all? Okay. Well, the next thing that we're going to talk about after the conveyors that's going to be part of this exercise is the storage object or the racking system object. But I don't want to get into it with only 15 minutes to go. So would it totally break your guys' heart to end a little bit early today?
Oh no! I guess I'd be okay with it.
Somehow
What
we'll
are you gonna do
manage.
with the extra 15 minutes.
Bourbon.
All right, guys. Well, thanks for hanging in there again today. I know I've thrown a lot of information at you. So thanks for being here, and we'll see you tomorrow morning.
All right, have a good one.
See you later.
Thanks.
Good
Bye.
evening,
Thank
everyone.
you.